So, in the last session, we discussed about what is dimensionality reduction, right? So, dimensionality reduction is just that because of the curse of dimensionality in higher dimensions, um, because of the curse of dimensionality in higher dimensions, we were actually not able to visualize the data or apply any of the machine learning uh, distance metrics, the statistical metrics like distance or finding the correlation is no more valid in higher dimensions, right? So that is the reason we are trying to reduce the dimensions and we want to retain only the dimensions uh, which has more information or the variance of the data is more. So such kind of dimensions only we would like to retain going further. So the methods that we can use for this will be discussed today. So we also have understood what is intrinsic dimensionality and what is an extrinsic dimensionality also, right? So most of the data or the information will be residing within 2 to 3 dimensions. So such kind of dimensions are called as intrinsic dimensions. Whereas if you consider the whole dimensionality of the data set, we call that particular number as extrinsic dimensionality, extrinsic dimensionality. So starting with this particular slide today, now we want to understand how many types of dimensionality reductions can happen, right? So the first thing is feature selection, selecting the subset of the most relevant features from the original data set. So let's suppose, now we have like 100 dimensionality data with us. So what we can just go and do is pick only few dimensions out of that particular data. So we go pick some, let's suppose if I have 100 dimensions of data here. Um, so what I'm going to do is this is 1, 2, 3, 4, 5, so on. I have 100 dimensions of data with me. So what I can just do is I can just go ahead and pick some dimensionality out of it. Let's suppose this can be the dimension 2, this can be dimension 3. Just pick random 2 to 3 dimensions, or it could be n number of dimensions out of this. So what we will do is we will just ignore the rest of the rest of the dimensions completely. We will bother only about these 2 dimensions that we do have. Okay, so that is uh, that is what feature selection is. How do we select these two features is something that we're going to, we don't go randomly pick the dimensions, right? So we need to have some parameterization or some kind of calculation to pick those random dimensions out of these 100 dimensions. We need to make sure those dimensions has the high information or high variance is covered across those 2 dimensions. So how do we basically pick pick those few dimensions out of these 100 dimensions or n number of dimensions is something we will find out the correlation coefficient. Okay, so if I go back here to this particular slide, we want to predict house prices. Okay, so what is that being done? So we these are all different dimensions of that particular data set. So what are the dimensions that we do have? Size of the house is one of the dimension, number of bedrooms is one of the dimension, age of the house is one of the dimension. So now we have these these coming as the columns. Okay, so now our data set looks something like this. So this is our data set and it has different columns which we call as dimensions. Each column is each parameter here. So size of the house is one of the dimension, number of bedrooms is one of the dimension, age of the house is one of the dimensions, number of bathrooms, this. So these are all different dimensions in your data. Now what we have done is that we have found out the correlation coefficient of different dimensions. Okay, um, so we try to find out the correlation coefficient of different dimensions, and then what we will do is we will come up with the topmost correlation coefficient data sets. So if you consider these as the correlation coefficients of different features, Okay, so now what I have come up with, if I have to select only four dimensions out of these eight dimensions, what I'll do is I'll just rearrange the correlation coefficients in the descending order. Okay, and then I'll choose only the top four correlation coefficients. So out of these eight dimensions, what I have done now, I have chosen only the topmost four dimensions where the correlation coefficient is higher. Okay, so the 0.85 is the highest value out of this, 0.60 is the highest value which is coming next the third highest value is 0.40, and the fourth highest value is minus 0.50. Oh, is that not okay? 0.8, 0.6, 0.7, and then okay. And I'm choosing the negative correlation, right? So correlation always starts with -1, less than or equal to, this is the correlation coefficient, and 1. So when the value of the correlation coefficient is approaching to 0, that means the correlation between the variables is less. But when it is going close to 1, it means they are positively correlated. They are correlated, they are very strongly correlated, but in the positive direction. The negative one says they are strongly correlated, but they are negatively correlated with each other. So now here what I have done is I rearranged the values, and I have taken the topmost three values and uh, and the the negative value. It basically means the highest values, whether it is positive or negative. So what I mean to say here is that if you look at these values 0.15, 0.40, 0.20, 0.10, so we are ignoring all these four dimensions. The reason being, in terms of values, they might look lesser, or negative seems very less when compared to 0.4. But when it comes to correlation coefficient, it doesn't matter whether it is plus or minus. It what is all it matters is the value here, right? The reason being, the plus indicates positive correlation, but it is a strong correlation if the value is greater than, I mean, when the value is coming close to 1, but negative indicates uh, this is also strongly correlated, but in the negative direction. So we have to just arrange the values in the descending order, ignoring the positive or negative sign assigned to them. So what are the highest values? 0.85, 0.6, 0.7, 0.50. When coming to this correlation coefficient, minus 0.50 is not lesser than 0.40. The reason being, we are just considering the strength of that correlation, or the strength of the dependency on one variable with the other variable. That is only what we are gathering. If it is negative, it is just negatively correlated, but it is strongly correlated is what it means. So when you want to pick few dimensions out of n number of dimensions that are given, you will find out the correlation coefficient of those variables, and then rearrange them in descending order, and then you have to pick the topmost values, whether it is positively correlated or negatively correlated, and then you just have to you know like pick n number of dimensions out of this. Like if you want to just pick only two dimensions out of these data sets, you just have to pick the top two rows. If not, if you want to go with four, you can go with 4 5. It depends on how many dimensions that you want to retain in your data set. So the initial step would be find out the correlation coefficients, and then find out the topmost rows in that. So that is just feature selection. The name itself is saying like feature selection. We are just selecting some features out of the given dimensions, or I mean given features or dimensions, whatever it is. So this is rarely used. This is just the initial type of doing the dimensionality reduction, but this is something which is more important. We extract the features out from the dimensions given. So what does that mean is that we will not ignore any of the dimensions. Ignoring a particular dimension basically means that we are losing a potential information from the data set, right? We are completely ignoring that particular column values, which is not really good. So what we do in futures extraction is that we now transform the original points into the lower dimensional spaces. So original features into lower dimensional spaces means, so we here, if you take the same example, if we have 8 dimensions, so okay, right now what we are not in future extraction, what we do is we create new dimensions, or we find out new dimensions such that new dimension is the linear combination of the original dimensions. What does that mean? So let's suppose I have the 8 dimensions here, right? Now I want to find out a new dimension such that I mean the variance will be high in that particular direction. But for now, what you just have to understand is I'm going to find out a new direction such that new direction is a linear combination of the original dimensions. Okay, that means to say let's suppose 2 into size of house plus 3 into number of bedrooms. Okay, so this is called as linear combination, right? So we are combining the dimensions and getting a new dimension. And this way what happens is that we are constructing new dimensions by using the existing dimensions, and we are reducing the number of dimensions by some number. Right here we are reducing 2 dimensions into 1 dimension because we combined these 2 dimensions and created a new dimension. Okay, so that is what basically feature extraction is: creating new features by transforming the original features into lower dimensional space. Why it is becoming lower dimensional space? Because we are reducing the dimensions. How we are reducing the dimensions? By linearly combining the existing dimensionalities or original features. That is how we are reducing the dimensions. So how we actually achieve this is a different story, but here the most important thing is for you to understand what is feature extraction. The transformed features are combined of are the combinations of the original features. That is what we have seen. Okay, if you take this example now, just consider this example. Okay, what this these are the original features given to us: employee ID, years of experience, number of completed projects, team collaboration score. So these are all the original features given to us now. So these are the original features. And look at this. These are the new dimensions that we derived from the original dimensions. How we derived them? We just combined we just combined the original features and derived the new features. If you look at the performance score, which is a new dimension derived, how we derived that? We combined team collaboration score and technical skill score. So we combined these two features and came up with a new dimension. That dimension will be the new feature set dimension. So we transform the points from this space to this space. And how we are getting this new dimensions? By linearly combining the original dimensions. Similarly, if you take this experience effectiveness ratio, it is calculated by using the original dimensions. What are the original dimensions used? Number of completed projects, this is done, and years of projects. So this is also considered. So now we considered all these four dimensions in the original data. What is the other one? Overall contribution. Overall contribution is that attendance rate into annual salary. So we combine sixth and seventh now. So sixth and seventh futures are also combined. Okay. Now we combine the sixth and seventh futures. Now, what are we only left with? So sixth and seventh is also combined, right? Now we are only left with employee ID. There is no change in the employee ID. Employee ID remained as employee ID. So now we combined all the features. We used every dimension in the original data set, came up with a new feature set. So the new feature set is a linear combination of the original dimensionalities, but some of the dimensions also remain unchanged, right? So that is how we construct a new dimensionality set. This dimensionality set is 7. The dimensionality of this data set is just 4. So we reduced 3 dimensions from the original features to new feature set. So that is the difference between feature selection and feature extraction. Understood?
Yes, bro.
Yeah. So that is the difference between feature selection and feature extraction. Feature selection is just go pick some random dimensions from the data set. Just ignore the remaining data set. So there is a potential loss of valuable information or a good information from the remaining dimensions. Even though we calculate the correlation coefficient, the dependency between different dimensionalities and all that stuff, um, uh, we just pick the highest correlation coefficients, but when compared to the feature extraction, the loss of information would be more in feature selection. In feature extraction, what we are doing, we are just we are using every dimension in the original data set, linearly combining them and coming up with a new feature set. So this is where this is something which is more frequently used. And now, how to actually combine the variables, how do we come up with these values and all that stuff, how do we come up with this kind of expressions. So when you say, you know when you say you are creating a linear combination, that linear combination has to be effective and it should cover the entire data set, right? So it should cover the entire variance in the data. Okay. And the loss of information should be minimum. So how do we come up with these linear equations is something what we will actually try to study today. So PCA is one kind of technique used for feature extraction. Okay. And then let me, if I go back here, so feature construction techniques. So now we understood the different types of dimensionality reductions, right? Now the different techniques that we use to actually come up with those new dimensions. Okay. Um, so the first one is linear combination. The other one is non-linear combination. By now, you should be able to understand what is a linear combination. Linear combination basically means we are combining the original dimensions linearly, right? So this is a linear combination. We don't have exponential factors, something of that sort, right? E square or to the power of 2. We don't have such kind of stuff. It's just a linear combination of the data set, right? So it's such a kind of a technique is called as linear combination. So reduces the dimensionality. So we are talking about dimensionality reduction techniques. It reduces the dimensionality by finding the linear combination of features that maximize variance or preserve distance relationship. We will come back to this shortly. The combination of features. Until this, we are combining the features linearly to come up with the new dimensions, and those new dimensions would be less than the um, original dimension of the data, right? So that we are aware of. So that maximize what this new dimensionality has to do. It has to maximize variance or preserve distance relationship. So we will understand that shortly. But just understand there are two types. One is linear combination. Other one is non-linear combination. Okay. So why do we need to use non-linear combination? Is that when you have complex data sets, when the data set when the data points has more complex relations, and if you want to actually separate such kind of data sets, you cannot go with linear combinations. So if you look at the data here, there is a linear relationship between the data points, right? This is dimension 1, this is dimension 2. As x is increasing, y is also increasing. So there is a linear relationship between these variables or dimensions. That's the reason you are able to apply the linear combination technique. But is there any linear relationship between the data here? There is no, right? So as x is increasing, y has different values taking place, right? So they are not linearly related. They have some non-linear relationship between the data points. But if you look at this, so in such cases, we go with non-linear combinations, and these are the examples: PCA, SVD, and LDA. Principal component analysis, singular value decomposition, and linear discriminant analysis. So today we are going to complete learning of PCA. What PCA says, PCA will try to reduce the data from higher dimensionality to lower dimensionality. That is a technique which we will see today. What this PCA will do is it will find new dimensions, which is the linear combination of the original features or dimensions, and those dimensions will maximize variance or preserve distance relationship. Okay, we will get to know that what is that when you actually learn the PCA. So now if you look at this non-linear combinations, you cannot apply linear combination. For non-linear combination, what you just have to do is you have to apply some other technique. We call them as nonlinear uh, techniques, but just see this intuitively. But the whole target, the whole concept for now is, or the whole uh, target for now is to separate these two variables. Okay, we have to separate red dots with the blue dots. Let's suppose all the blue dots are dogs, all the red dots are cats. We should be able to bring all the cats at some place and all the dogs at a particular place, even if you reduce the dimensionality. Look at this. All the now they are scattered, right? The blue, all the reds are at one place, all the blues are around the reds. So if I have given black color to all the dots, you cannot actually predict what is dog and what is cat, right? As I have given colored, you are able to visualize which class a particular uh, point belongs to. Now the main goal here is I want to transform this data from this to this. Look at this, all the blues are separated, all the reds are coming at one place. How am I doing this? Just visualize this. How I am doing this, I just have to separate these points, right? So how I am actually doing this is, if you look at this diagram, I am lifting all these points into the space, into a 3D space. This is a 2D space, and now I am moving all these blue dots to a 3D space. So these will remain there. The ones that are surrounding to the red will go up, much up. Look at this. All the blues are floating in 3D space at a great height, whereas all the red dots remain in the at lower heights. This is what happens when you move the points, or elevate the points into 3D space. And then what I'm doing here is I'm putting a 2D space again here. This is my 2D space, and I'm projecting all the points onto the 2D space. Now what happens is that all the you know now I elevated these points to 3D space based on some criteria, let's suppose, so that all the ones, let's suppose if I take this as a center, it depends on the distance from the center. If the distance is more, it will move further up in the 3D space. Okay, if the distance is less, they will go very little height in the 3D space. Okay, so now if you look at this, all the points which are at less distance from the horizon is going very little up in the 3D space, which is very far, is going very far from the mean, or the middle point in a 3D space. That's how we are actually elevating these to 3D spaces. And once these are elevated, what you are doing here is that you're placing in another 2D space here. Okay, perpendicular, I mean opposite to that. And now we are projecting all these points onto this 2D space. Okay, when you project all these points into 2D space, you're converting 2D space to 3D space. So now the points are looking like this. Okay, some way you're able to separate those 2 points now. So all the reds come on one side, all the blues came on one side. Now I'm again placing in another 1D space here, and I'm projecting these points onto this 1D space. So finally it looks something like this. Okay, understood? So that is what nonlinear
Yeah.
combinations is. This has to be achieved using nonlinear combination. You cannot go with linear combination. So we call these as kernel PCS, and we will also study about the techniques. I mean the technique related to this. Okay. techniques related to the kernel PC as well. So that these are different feature construction techniques. One is linear combination. In linear combination, what we do is in linear combination, what we actually do is we will just get a new feature, and that new feature would be a linear combination of the original features. Okay. And in kernel PCA, we use non-linear relationship between the points. And it's a different kernels are a different techniques. We elevate the points into an additional space, and from that additional space, we will again bring them down to the lower dimensionality sets. That is the only way you can actually, separate the points, or else it's nearly impossible to actually separate the points if they are not if they're not linearly related. Okay. And if I go back to the next slide, so I hope you understood this, right? Linear
Yes.
combination and non-linear combination. So now we go back to,
Foundation.
yeah, now we go to the other slide, which is finding the maximum and minimum in a data set of a particular function. Okay. So just a second. Now we have to learn about finding the maximums and minimum calculations of a particular function, because these are useful later for our understanding different techniques. So we will cover this and move forward. This is just a mathematical concept, so you should be able to easily grasp this. So if you're given a function, okay, this is the function that is given to you, and that when if you represent that in a 2D space, this is how it actually looks like. So if you look at this, you have to find out what is local maximum. What is There are few terminologies that are available here. The first one is local maximum, the second one is local minimum, and the next one is global maximum and global minimum. Okay. Global maximum and global minimum. So just by looking at just by looking at the graph, you can simply say like local maximum or local minimum is any point where there is a maximum and where there is a minimum. But global maximum and global minimum is that um, uh, is a point where you have the maximum of all the peaks. Okay. And global minimum is something like where you have the minimum at all the peaks. Okay. So if I take an example like this, just take another example. If I have something like this, okay, all of these will become local maximums. Okay. This will become global maximum because it is the highest peak in the graph. These are all peaks only, but these are not the highest. So we call them as local maximums. And these are all local minimums. And this is like global minimum. So the highest peaks are called as globals, and the others where we have peaks are called as locals. So we always have to find out, we here the whole intention is given a particular function, we are just trying to find out the global maximum, global minimum, local maximum and local minimum. Okay. So that is all what you have to do right now, and how we actually achieve that is what we will see in this particular slide. Okay. um if you just give me 1 second, I'll. Okay. So now our whole intention is to, given a function, we just want to find out the local minimums, local maximums, global minimums, and global maximum. We can have any number of local minimums and local maximums, but we can just have one global maximum or one global minimum within given a function. So now let's understand what actually the ways of finding local maximums and local minimums, but let's try to understand this intuitively. So if you look at this, this is something which I would
Screen is not
try
shared.
to explain to
Screen
you.
share.
So
Screen
we
share.
know like what integration will basically do is it will try to find out the area under the curve, right? That's what we have discussed and when we are trying to understand about probability density function. Okay, now in this case, what integration basically will do is it will just try to find
Screen
out
is not shared, mom.
the slope of a given curve. Okay, so that is what it actually will do. So given this curve, this is my curve given to me. Now I'm trying to find out the global maximum and global minimum or local maximum or local minimum for this particular function. So now what I have done is I have calculated the derivative of the given function. So this is the function which is given and I found out the derivative of this particular function. And then if I plot this particular function, this is what I have got. Okay, so this is the graph which I have got if I plot the derivative of this particular function. So what this says is this is nothing but the slope of the this particular curve at any given point. Okay,
Screen share
you
is
know
not
the
done.
slope of a line parallel to
Screen share is
x-axis
not
is
done.
zero, right? It's a slant. A straight line will have a slope of zero. So calculating a slope at any given point is just like drawing a tangent line at that particular point, right? So this is the tangent line at this particular point. If you look at the slopes at this point, at this time, at this side, it's a straight line. So the slope would be automatically goes to zero at this point, right? A straight line will have a slope of zero that we all know.
Slope.
Okay, that's the reason. So if you look at this particular graph, which I'm saying will give you the slope of this curve at any given point. Just to just to agree with that, if you look at any specific point, if you look at this point, the slope here is zero because the tangent line is a straight line here. Okay, so the derivative will always gives you the a slope of a given function. So that is first thing that you have to agree with. Okay, so when you plot, when you take the derivative of any function, it is just gives you the plot of the slope of that given curve. And what happens when you take the double derivative of a particular function? Okay, now double derivative is nothing but what it will actually give you. It will just
Screen
give
is
you the
not share.
slope of this particular curve, right? Derivative will anyways give you the slope of a given curve. Now our main function is nothing but our first function would itself be, let's, if you consider this as a function, if you apply derivative for this, we will get the slope of that particular curve. But if you already took this is just a derivative of this initial function. If you apply double
Screen
derivative
share
for
is
this,
not done.
it just means applying the
Screen is not shared.
calculating the slope of the, I mean, slope of the first derivative. Double derivative is nothing but calculating the slope of the first derivative. Now, this is the curve. And for this curve, if you take the slope at any point, you will actually get the slope of this curve. This green line is nothing but the slope of this first derivative. Okay. So where do you guess the slope will be zero for this particular curve?
Screen is not shared.
Yeah, Chintu, hello.
Screen is not shared, mom.
Screen is not shared.
Oh, sorry.
Our voice is audible to you.
No, I just muted. So, okay.
Okay.
So that's the reason we shouldn't do on the weekdays, actually. Okay, let me just come back to this again. So what we are trying to find out here is the local maximums and local minimums, right? That is what we are actually trying to find out here. So we know what is a local maximum and local minimum, right? We already understood that. Uh, did we discuss this before we stopped this, or what? You understood what is a local maximum, local minimum, global maximum, global minimum?
Yeah, Mon.
Yeah. So now let's take an example of a particular graph. This is the graph that we do have. Okay. So let's if you take this particular graph f of x, if you apply derivative for that particular function, what happens is it gives you the slope of that particular line at any point, at any given point. Okay. So this is the original graph. Okay. So this is the original graph, and to that graph, we are actually trying to find out the slope. Okay. Are you able to see my mouse pointer?
Yeah.
Yes.
Okay.
Yeah. Yes.
So now this is the given curve for us. And when we calculate the derivative of that particular function, we got this. And if we plot this particular function, we actually get this particular graph. This graph is nothing but slope of this graph at any given point. So just to prove that, if you actually take slope is nothing but the tangent line at any given point, right? So we all know here is the straight line. Okay, this is a straight line here. So if you want to take the slope of the curve at this point, this is when you draw the tangent line, it is, so the slope here would be equal to 0, right? This is a straight line to this curve. So if you just go back to this original curve, this is touching 0 at this point. The value is 0, right? Slope of that given curve. Similarly, at this point also, it is actually touching the value 0. Got it? Hello?
How it is zero, Mon? I
Yeah.
didn't
How
understand.
So the slope of any straight line is 0, right?
that is tangent? No.
Yeah, this is tangent line. When you want to calculate slope at any given point, you will draw a tangent line to that. And that tangent line, if it is a straight line, that slope of that straight line would be equal to 0. Uh,
Slope of the straight line is 0, but tangent, the curve slope is 0.
so when so just try to understand the scale this way. Okay. So I'm coming back here. Given a function, when you take the derivative, it's said that you will get a slope of that particular curve, which is f of x. To actually prove that, what I have taken is I have taken a specific point where you're getting a straight horizontal line. I mean, a horizontal line. Okay. So at this point, if you see the slope, you know the slope at this particular point is 0. So if you look at this, the slope is 0. How to actually interpret this is, interpret these dimensions is, for this curve, when the x value is 3, these indicates the value of the function. The values, these are the values of the function all together. Okay, these are the x values for this particular function I'm talking about. If you take x is equal to 3, okay, and I substitute here, 3 square is equal to 3 square is 9, 2 into 3 is 6, minus 6 minus 3, total will be 0. So the value of function at that particular point is 0. That is how you have to interpret this. If you substitute x is equal to 0 into this point, at that particular point of time, what is the value of the slope? What is the value of f dash of x? This is f of x. I'm just talking about this graph and this scale. How to interpret this scale for this graph is what I'm saying. It looks confusing. You might think at this point the value is 3. That's not right. So these are the x coordinates and these are the values of f of s. I mean derivative of x. Okay. So if you substitute x is equal to 0, what is the value of f dash x? It is minus 3, right? So if you look at this particular point, this point, it is minus 3, 0 to minus 1, minus 2, and minus 3. Okay, so this is minus 3. So these are the values of f dash of x, the values on the x-axis. These are x values. Okay, that is all what it is. So this is the when the tangent line is parallel, I mean when it is a straight line, the slope of the tangent line at a given point is the slope of that particular line. Okay, so the slope of this line is 0 at this particular point and also 0 at this particular point. What you just have to understand is, uh, to find the critical points, we call them as critical points, whether it is local maximum, global maximum, these points are called as critical points. To find out the critical points, what you can just do, at critical points, you can see the derivative is 0 at any given point. Okay, even the graph, basically, if it is actually looks like this, at every peak, at every critical point, the slope will always be 0, because when you draw a tangent line at that particular point, it is a straight line, so the slope will be actually equal to 0. Okay, understood? Hello?
Yeah,
Yeah.
Yeah.
yeah, understood.
If you still want to get more clarity on it, so if you take the 2D coordinate system, this is horizon, right? This is 1, 2, 3, and this is 1, 2, 3. How do we represent this particular line? What is the representation of this particular line? It is y is equal to 1, right?
X, yeah, I is equal to 1.
Y is equal to 1, or do we have anything else? Or else, do you know the formula for slope? Slope is not just equal y2 minus y1 by x2 minus x1, right? Is that right?
Yes,
When any
y2
two
minus
points are given,
x2 minus x.
what is the actual formula of slope? It is y2 minus y1 by x2 minus x1. Just take any 2 points here. What are the 2 points? 0, comma 1. And what is the other point here? Uh, Sorry, it is 2, comma 1, right? This, let's, if you take 0, 1, 2, what is this point? It is 0, comma 1, right? This point is 2, comma 1, right? Is that right?
Yes. Yes.
So
Yeah,
y2
yeah,
is 1 minus y1 is 1 by x2 is 2 minus y2 x2 is 2, y2 x2 is, I mean, x1 is 0. So 0 by 2 is 0. So slope is equal to 0. Is that clear now? So any line parallel to x-axis will have slope equal to 0. Is that right?
Yeah.
Yeah.
Yeah. So now the slope at this particular point is 0. The slope at this particular point is 0. Okay. So this is 0 and this is 0. So even if you take any critical point, the slope at that particular point will always be equal to 0. So to find out the critical points, what you have to do now, you have to take the derivative and you have to make that equal to 0 so that you will get all the critical points. Critical points are nothing but local maximums and local minimums, global maximums or global minimums. Okay. Is that clear?
Yeah.
Yeah. Clear.
Yeah. So that's how you find out the global maximum, I mean the critical points basically. Now you have to find out whether that particular point, whether that critical point is maximum point or minimum point, and also you should be able to find out what is the whether a given point is global maximum or local maximum. That is what you have to find out, right? So with this first step, what you are able to find out, you are able to find out the critical points. The main property at the critical points is the slope of the points at the slope at critical points will always be equal to 0. So what you will do is you take the derivative and equate that to 0 so that you will get some particular points. At those points, we will have the slope is equal to 0. So those points are nothing but the critical points. If you solve actually this particular function x square minus 2x minus 3, you get x square. So if you solve this for the x values, what you will get? X square minus 3x plus x minus 3. So this actually gives us x is equal to 3 comma minus 1, right? So if you look at this, this is one of the critical points, 3. Minus 1 is the another critical point for this function. So what you have just done, you have taken the derivative and equated that to 0. And now you have to find out whether 3 is maximum point or minimum point, minus 1 is maximum point or minimum point. Now what I have done is I have taken the double derivative for this particular graph. For this graph, double derivative is nothing but slope of the first derivative, calculating the slope of the first derivative. So this is the first derivative and I'm finding the slope of the first derivative, and that gave me this particular line. Okay. Now what I'm trying to do is, look at this. I'm putting forward the main graph and also the double derivative that we have obtained now after taking the derivative for the first derivative or calculating the slope of the first derivative. Now, if you carefully observe, at maximum points, the double derivative is less than 0, right? And at minimum points, the double derivative is greater than 0, right? Is that right? Till this point, we have values less than 0. After this line, we have values greater than 0. Okay. Where is that?
Yeah.
I have something to show you. Point options bin. Okay. Maybe just look at this particular thing. So look at the m values here. So m is gradually, what is happening to m here? Just look at the values of, just concentrate only on the values of m. Let me just clear everything. Okay. So just focus on the values of m here. Now the value of m is 14.05, right? Are you able to see my screen? The values of m here is 14.05. Here it is 10.21. Here it is 5.41. It's 0.46. Now look at this. The value till this point, till that point, is keep on decreasing, right? Here we have seen 14, 10, so on. It keep on decreasing till this point. And if you look at the values of slope from this point, it is gradually increasing. Look at the values of the m. They are increasing, right? 3.36. So again, just look at that. So now we have m. So the value will gradually decrease slowly. It's decreasing, decreasing, decreasing till some point. Till some point it keep on decrease. Till that point it is decreasing. Now it is slowly increasing again. Okay. Now from here, where the double derivative is equal to 0, okay, look at the double derivative is equal to 0. At this point, the double derivative is equal to 0, right? After that particular point, what happens is the slope will increase. Okay, if you go down from that particular point, the slope will keep on increasing. Okay, look at that. So from there, the slope will increase. Understood, right? So till some point, when we start from one particular point, the slope is gradually decreasing till a particular point. And if you look at that particular point, at that particular point, the value of double derivative is equal to 0. Okay, that is called as inflection point. From inflection point, the slope will again increase. That is what this graph, that is what you have seen just now. So let me just go back. So when you're coming from here, the slope gradually decreased till a particular point, and that particular point is nothing but where the double derivative is equal to 0. And that particular point where double derivative is equal to 0 is called as inflection point. And from that inflection point, if we move forward, if you have local minimum, the slope will keep on increasing. Okay, at this point where double derivative is equal to 0, the slope till that point it got decreased as we have local maximum, and from that point it will keep on increasing again. So look at that values 3 point, it's negative value but it increasing, it slowly goes to 0, and then it as the slope is increasing here, the slope will go up. Okay, so such a point is called as inflection point. Where the double derivative is equal to 0 is called as inflection point. Now at local maximum, what happens? Double derivative will be less than 0, right? Okay, this is concave down, this is concave up. The slopes will keep on increasing from the inflection point when you have concave up. At concave down, the slope will keep on decreasing. So till you reach if you have something like inflection point. Inflection point is something where double derivative is equal to 0. So if you take this particular peak maximum, what you're finding, the double derivative is less than 0. So what you can say, when the double derivative is less than 0, you can say that particular point is maximum. When the double derivative is greater than 0, and the double derivative value is greater than 0, you can say that as local minimum. It is opposite. Now did you understand what is the intuition behind saying like if double derivative is greater than 0, that is local minimum, and if double derivative is less than 0, that is local maximum? And you should also understand what is inflection point. Is this clear?
Yeah, clear.
Yeah. Till that inflection point, the slopes are gradually decreasing. And at a point where double derivative is equal to 0, you are getting, I mean, the slopes are gradually increasing again. Okay, when the slopes are gradually increasing, that means you have concave up here. Concave up is like this portion is called as concave up. This is called as concave down. Okay, when you're approaching the concave down, you are getting a local maximum, and in concave up you will gather local minimum. At inflection point, double derivative will be equal to zero. From inflection point, as the slopes are continuously increasing, you can say that as local minimum. So to keep it, this is just an intuition, but basically when you are trying to find out maximum and minimum calculations, what you'll do is take that function and do the first derivative. You will get the, critical points. And now if you want to find out whether at a particular critical point you have local maximum or minimum, you do the double derivative and apply that critical point value of x. And if you find out that double derivative is greater than 0, you can say that as local minimum. If double derivative is less than 0, you can say that as local maximum. If double derivative is 0, you cannot actually predict whether that is local maximum or minimum. You say that as inflection point. And this is the intuition behind saying these statements. Okay. And this is the intuition behind saying like derivative will give you the slope of a particular graph. Okay. And if I go back to the next slide, this is just an example. Given me a function, the function given here is f of x square plus 4x cube plus 4x square. I took the derivative of it, and now I will calculate the critical points by equating this to 0. Why I equate this to 0? To get the critical points. Hello?
Because slope is 0 at those points.
Yeah, slopes is the function itself, and the slopes will be equal to 0 at that critical points. So this equation is just the slope curve. So this curve will be 0 at the critical points. So we are equating that to 0 and finding out the values of x, 1 and 2. Okay, so what he has done, he has taken 4x as common. This becomes x square minus 3x plus 2. So you can just say minus 2x minus x plus 2. So x becomes 1 and 2. So now we have the critical points as x is equal to 0, 1, 2. Now we want to know where we have local maximums and where we have local maximums. Okay, so I'll take the double derivative of this particular first derivative and I apply x is equal to 0. As this is greater than 0, we call this as local minimum. As this is less than 0, just apply the critical value into this double derivative function. And x is equal to less than 0, so it is local maximum. And when you apply x is equal to 2, you're getting greater than 0. So at x is equal to 2, it is local minimum again. So where we are getting local minimums, x is equal to 0 and x equal to 2 are the local minimums. Where is the local maximum? At x is equal to 1, we have the local maximum. Okay. Now, where is the global minimum? Is that at 2 or 0?
2.
Why?
Because it is the maximum value, like comparing between the two minimums.
No, it's not this two. You just have to find out this value, right? Double derivative. When any of these values are greater than a specific value, I mean, if this has 12, then this will become the global minimum. The double derivative value decides which is the global maximum or global minimum again. Okay, I don't
Okay,
get that example. Sorry. So that actually gives you the local maximum or local minimums. Okay. So the double derivative value, the double slope value, this value has to be more, right? For this to be global maximum. If there is much more graph like this would go just stop. Okay, this would be more, right? As it keeps on increasing, it will be like it will be more steeper value. So you will get more f double dash of x value there. Is that right? So f
yes.
double dash x value has to be whichever function has, I mean, whichever critical point has more f double dash of x value, I mean, the slope is more, then there you will have the global critical point. I mean, global maximum or global minimums. That's how you find out the global maximum or global minimums. Understood?
Yeah.
Okay. So if I go back to so this is the function given. We are taking a derivative and we got two critical points, x is equal to 0 and x is equal to 2. And we took the double derivative and we got, what is the double derivative? 6x minus 6. And we applied 0 here and we got minus 6. And we applied 2, we got 6. So now where we should have the global maximum? Of 0 is equal to 4. These two are local minimums. This is local minimum. You just have two critical points. Okay, so basically you just have to find out, I should have kept that function. You just have to find out the double derivative of x and then that value will decide which is global maximum and global minimum again. Okay. Let's come back to that again. I'll just show you another example tomorrow. So now we are trying to find out the local maximum and local minimum, right? And now if you want to find out the local maximums and local minimums with constraints. So now we are trying to find out the values of x and y, right? I mean, you found out the value of x, which are critical points. And now if the critical points cannot accept all the values, okay? If let's say your critical point x shouldn't accept 5, okay? That is a constraint. In the previous example, you have got x is equal to 0 and x is equal to 0, 1, 2. If I have a constraint saying that if the critical point shouldn't be equal to 2, okay, um, that is called as constraint. Limiting the values of the critical points is what actually a constraint basically is. So the method of so for solving such kind of problems, we use Lagrangian multipliers. The method of Lagrange and multipliers is used to find out the maximum or minimum of a function. So these are also used to find out the maximum and minimum of a function subject to one or more constraints. What is a constraint? Constraint is just a restriction or condition that limits what you can do. It limits the values of the critical points. So this is just an example of that constraint. Like this, if you're trying to maximize your profit, but your budget is $100. So the budget is a constraint to your problem. So when you have such kind of constraints, how to find out the maximum and minimum value of a particular, I mean the maximum and global maximum or whether it is local maximum, finding out the maximum and minimum values of the function is to find out those uh, maximums and minimums, we use Lagrangian multipliers when you have a constraints. So given a function that you want to maximize or minimize is called as objective function. Okay. So the function to which you want to find out the maximum or minimum is called as the objective function. So constraint is a condition that variables must satisfy. So these x and y values, which is the maximum point or minimum point, should satisfy this particular function. If not, that cannot be a critical point. Okay, so it should satisfy this constraint. And Lagrangian multiplier is a scalar introduced for the constraint. So using these Lagrangian multipliers, we will actually solve the x and y values with the constraints. So the overall function would be written this way. Lagrangian function of x, y, lambda is f of x comma y plus lambda into constraint. Okay. Here f of x, y is objective function we know. G of x comma y equal to 0 is a constraint function. Lambda is a Lagrangian multiplier. How do we solve this is, we solve this by first we construct the Lagrangian function and then we do the partial derivatives with respect to x, y and lambda, and then solve the equations. Solve the partial derivative equation that we got by equating that to 0. So it is as simple as, if you take this example now, so I have got this function. This is the objective function for me, f of x plus y, subject to constraint. The constraint is x and y values that we are getting as critical points should satisfy this function. If I substitute x and value, so they should be equal to 1. Okay, so that is my objective function. Now, if I have to constrain the Lagrangian, so the objective function is this, which we want to maximize. The constraint is, which represents a circle of radius 1 centered at the origin. This is the equation of a circle. So the point should lie on the circle with radius 1. So the Lagrangian function is nothing but f of x plus y plus lambda into g of x plus y. So f of x, y, x comma y is x plus y, plus lambda into g of xy is x square plus y square minus 1. Okay, g of xy would be equal to 0, right? So we have to take this minus 1 onto the left hand side and we have to take this function. Okay, then it becomes g of x comma y equal to 0. Okay, so now we need to take the partial derivatives of this with respect to f of x. That would be the second step. If I take the partial derivative with respect to x, what I'll get? X, so this will be 1, this is constant 0, and for this it is 2x lambda, and this will also be constant with respect to x. So this is my first equation. And taking the derivative with respect to y again, so x would be constant with respect to y will be 1, lambda x square will be constant, minus 1 is constant, so only remaining part is y square. That becomes lambda into 2y is equal to 0. The third one is, we have to take, you saw the steps, right? You have to take the derivatives using with respect to x, y and lambda. So I'll take the derivative with respect to lambda now. So that becomes, so this will be constant with respect to lambda. So I'll get x square plus y square minus 1 as when you take the derivative of lambda, because this is like constant and lambda will be 1. So these are the three equations that I have got now. Now I have to solve these three equations. Okay, the first equation is 1 plus 2 lambda x is equal to 0. So the lambda becomes minus 1 comma 26. 1 plus 2y lambda is equal to 0. Lambda becomes minus 1.25. I'll just take minus 1 this side by 2 lambda. So lambda, so these two are equal. So I can equate the right hand sides. So when I equate the right hand sides, I got x is equal to y. And now I substitute this in the third equation, which is x square plus y square is equal to 1 is what I have got, right? So when I substitute but x is equal to y here, I got x is equal to plus or minus 1 by 2, y is equal to plus or minus 1 by 2. Now we got two solutions. We also know x is equal to y, right? So when x is equal to 1 by 2, y should also be 1 by 2. X is equal to minus 1 by 2, y should also be equal to minus 1 by 2. Now we got x and y values. Now we substitute these values in the function, in the given function x plus y. So f of x comma y is root 2. F of x comma y is become minus root 2. So the maximum for value of f of x y is subject to constant is root 2. The minimum value is minus root 2. Okay, sorry, I think I misspoke here. So to find out the local maximums and local minimums, when you know that is local maximum and local minimum, so you have to apply those points in the main function, not in the second derivative. So if you apply 0 here, what you're getting? You're getting 0. When you apply 2 here in the main function, what you're getting, 2 to the power of 4 is 16 minus 32 minus 16 plus 4 into 16. It's also coming to be 0, right? When you apply in the main function. So once you got to know whether a particular point is local maximum or local minimum, to find out the global maximum or global minimum, what you have to do is take this point, apply in the main function. So if I apply 0 here, it becomes 0 minus 0 plus 0. So that will be 0. When I apply 2 here, 2 to the power of 4 minus 4 2 cube plus 4 2 square, right? So what this becomes, 2 to the 4, 16, this is minus 4 into 8 plus 4 into 4, 16. So 16, 16, 32, 32 minus 32 will be 0. So even this is also coming to be 0. So they both will become local minimums. When you asked about global minimum, there is no global, when you just have multiple local minimums, there won't be any global minimum. So because you have multiple local minimums. So basically you just have to substitute this in the main function, and then that value will says what is the maximum value of that particular function and what is the minimum value at this particular function. And this maximum value happened um, at which point? At root 2. Yeah. So when you x is equal to 1 by 2, y equal to 1 by 2. So you applied that and you got that as root 2. That is the maximum value for that given function. So this is quite. So we got the x and y values we got, and then we are substituting them in the main function. The maximum value is this and the minimum value is this. So here in the Lagrangian multipliers, I just need to revise this. So in the Lagrangian multipliers, we are trying to find out the values of x and y, which are like the constraints, which are like the variables to which we are trying to find out the values. Here in this is a given function where we tried out the local maximums and local minimums. These are also the maximum and minimum points. So the Lagrangian multipliers or partial derivatives will comes into picture only when you have only when you have multiple variables, or so that is when the partial derivatives actually comes into picture. When you are trying to find out when you are trying to apply calculus on multiple variables, then you do the partial derivative. So when you do partial derivative, the other variables will looks like constant, and only the variable with which you are doing a partial derivative, um, uh, to that particular variable only you apply the derivative. That is how you do the partial derivatives. Okay, so this is one way of solving the Lagrangian using Lagrangian multipliers when you have constraints. So when you have constraints, you have to construct the Lagrangian equation, and then you have to what you have to do, you have to differentiate that using all the variables and also with the Lagrangian multiplier and equate that to 0. And then you have to derive the values of all the variables and apply the variables in the main function to know what are the maximum values and what are the minimum values. So the one which has the highest value will become the global maximum, and the one which have the lowest value will become the global minimum, and the rest the local maximums and local minimums. Okay. So that is what Lagrangian multipliers basically is. So we learned finding out the maximum and minimum values just to understand this principal component analysis. The intuition of this principal component analysis, which is a dimensionality reduction technique, comes under feature selection. Will all depends on those concepts like Lagrangian multipliers, finding out the maximums and minimum values. Okay. So if I just let me just make it figure here. So we came back to principal component analysis. Everything that we have learned so far, the maximums and minimums, the Lagrange and multipliers and all, is just to understand the intuition behind principal component analysis. So we all know what is principal component analysis. Principal component analysis is a dimensionality reduction technique. So dimensionality reduction is it will just reduce the number of dimensions in the original space, and it transforms those n number of dimensions to some lesser number of intrinsic dimensionalities, right? So that is what actually principal component analysis will actually do. Principal component analysis is a statistical method used to reduce the dimensionality of the data by transforming it into new set of variables. So what are the new set of variables? New set of variables are nothing but the linear combination of the original variables, right? The principal components which are uncorrelated and capture most of the variance in the data. So those new set of variables are called as principal components, which are uncorrelated. Principal components are uncorrelated. That means they will not have any relationship. Are you able to hear me?
Yes.
Okay.
Yes.
Those principal components are uncorrelated. What is uncorrelated means they will not have any relationship between those variables, right? So those are uncorrelated and capture most of the variance in the data. What is the variance? The spread of the data from the mean is called as variance. So these principal components are the components or the lines or the axes which are uncorrelated but captures the most variance in the data. How they capture the data and all that stuff, we will slowly get to know about all of them. So principal components, what are the principal components? New directions along which the data has the most spread or variance. So now what we have the original dimensions. From the original dimensions we are getting new directions. Okay, new directions or new dimensions, we are getting new dimensions where the data has most spread or variance. Okay, so we are trying to find out the directions which has most variance and the spread. So you will get to know about what is this new directions along which the data has most spread or variance shortly, but that is what principal components actually is. Now let's go or let's study this with an example. So I have this gene 1 and gene 2, right? These are my dimensions and these are my different points that are there with me. So I have 6 different mouses. So these are called as points. Okay, these are dimensions. Now if I represent these points on a 2D graph, so now I am taking all these points and representing it 10, 6, 11, 4. So this is 10, 6, this is 11, 4, 8, 5, this is 8, 5, and this is 3, 3, 2, 2.8, 1, 1. Something like this. Okay, so these are 6 different points I have got from I have represented this data. Now what I have done is I have taken the mean of these points, okay, and I represented this as the mean. This is the mean of the points. How do I calculate the mean? I'll calculate all these values. I'll sum all these values and I'll divide this by 6, and I'll sum all these values and divide this by 6 because the number of points is 6, so that I'll get a mean. Something like, so let's suppose what is the value of this? 10 plus 11, 8, 9, 10, 20, 30, 38 by 6.
5.83.
5.83, something like 5.83 or 5.83. I would say some random value. So that is the mean, right? Now we have to do standardization. What is standardization? Standardization in terms of normal distribution is making the mean as 0 and standard deviation as 1, right? Why we do standardization is we don't want the values impacting the analysis. When I say values shouldn't impact the analysis means Let's take this example. Let's suppose I have two columns, simple columns, okay? I have two columns. This is my dimension 1 and this is my dimension 2. If I say the dimension has values of 1 comma 2 and the dimensionality 2 has 101 and 102 values. So look at this. This has very numerically very high values. That doesn't mean that this dimension is important to us, as they have high weight in terms of numbers, right? That is how their values are spread. Like if you take the height and weight of the persons as the dimensionalities, weight cannot be 101 or 102. They will be just 5 feet and 6 feet. But weight cannot be 5 kgs or 6 kgs. It has to be 100 kgs and 101 kgs, right? So when you take the numerical values, they give a sense that, or the model will think of them as, like very high important parameters. As the numerical value is high, the model may, or the technique may think that as most important parameter. We don't want that to happen. What you have to do is you have to normalize them. So what happens when you normalize them? They all comes to the same scale. That means mean is becoming 0. So just take the example of this. If you take the mean of this, what happens? 1 plus 2 by 2 and 101 plus 102 by 2. So if you subtract these values, these means from these values, now what actually happens is, now just look at how the new values look like. So what is 1 plus 2 by 2? 3 by 2, which is 1.5, right? So this is 1.5, right? 3 by 2 is 1.5, right?
Yeah.
So now let's take the mean of the other dimension, which is 101 plus 102 by 2. This became 101.5, right? So what you are doing right now is subtracting the mean from these points. 1 minus 1.5 becomes minus 0.5. 2 minus 1.5 becomes 0.5. 101 minus 101 minus 0.5 becomes 0.5. 102 minus 101.5 becomes 0.5. So now when you subtracted the mean from these data points, they all transform to a single point. Now model, as they all came into the same scale, the model will give the same importance for every dimension. So if you look at this, these values says that it has higher value, but when you normalize or standardize this, they all looks the same and model will gives the same importance to all the dimensions. So that is the reason you have to actually standardize the data before doing any kind of analysis on the data. If you don't standardize the data, maybe different dimensions will have different values or different scales of numerical values. And if you don't standardize, those values will definitely impact the outcome, which you don't want. You want the technique or the model to give the same importance to all the dimensions. That's the reason you have to standardize the data. Standardize the data is just nothing but subtract the mean from every value in your data set, so that all the mean will be centered and the data points will just move to the other side, some left or right. That's all. It will not actually change the distance between the points, or it will not do any such sort of stuff. The only thing that it will do is it will just move the points. Now, does that make sense why we have to standardize the data before doing any kind of analysis or any kind of stuff on the data?
Yes.
Okay. Now we are doing the same kind of thing here. So this is a visual representation of it. Now we represented these points on a two-dimensional space. Now we have two dimensions, right? Gene 1 is first dimension, gene 2 is second dimension. So this is my gene 1 dimension, gene 2 dimension. It is just like X and Y, but the names are given different, which is gene 1 and gene 2. How I represented all these points in this two-dimensional space and I calculated the mean. Now I transform this data, I standardized this data so that mean will become 0 and all the points will move towards the downward side. So when I'm moving the mean from this to this, what happens? The points will move slightly towards downside, right? So as as this mean is moving this side, this move, I mean these points also move towards this side, right? And these points also move towards this side. So that is what actually it happened. So these points got transformed here, the mean came to 0, and these points moved here. Understood?
Yes.
Even if you look at this, what after standardization, what happened? It becomes 0.5 minus 0.5, 0.5 minus 0.5, 0.5. What did the mean came here? Mean is just 0. Mean is just 0. So once standardized, we are just trying to make the mean of the new data set as 0 or standardized data set as 0. That is what we are just trying to do. After standardization, mean will become 0. So the points will, as we are subtracting the mean from every point, so they will just move downwards here. Okay, as the mean is moving towards 0. So that is the first step of the PCA analysis. When you are doing, the main goal of the PCA is to reduce the dimensionality by incorporating the variance of the data, most of the spread or variance in the data. Spread and variance are the proportional terms, right? They are equivalent terms, spread or variance. So we are trying to find out the new dimensions. So doing that, when you're trying to find out the new dimensions, the first step is to standardize the data. After standardizing the data only, you have to do any kind of actions on that. Now the next step, the second step is, so this is very important. The key objective of principal component analysis. You have to understand this very clearly. Now what we are trying to do, this is our new standardized data set, right? What we are trying to do here, all that we are trying to do here is, we are trying to find out, um, you know, um, the new dimensions. Okay, we are trying to find out a new dimension which will actually has the, I mean, which will rightly represent this data set. Okay, um, which will rightly represent this data set. I'm trying to find out a new component which covers the most variance in the data or spread of the data. So this is the two-dimensional representation of my data set. Now what I'll do, I'll just play this thing and just try to understand that. Now I have got one line. So does this represent my whole set of data? Is this effectively replicates my data? Just visualize this. So this is not, I mean, I have all my points somewhere and this line is somewhere else. This is not a good line for my data. This is not a good line for my data. So let's try a different line. So is this a good line? Is this a good line? Is this a good line? Just keep on rotating the line, and at some point you will find that as a good line. So this is a good line for the data set. Why I'm saying that is, so it is covering the most variance in the data set. I mean, all the points are lying close to this line, right? When you draw a other line, all the points are much farther to it. So this line, if you take this particular line, this line, all these points are much farther from this, right? But when you take this line, every point is close to it, right? Almost on the line. Some points are almost on the line and most of the points are close to this line. But none of the points are in the, if you take this particular line, what is there? None of the points are in this line, but every point is also far to this line. Okay. So that this is the best fit line is what I can say. At least do you agree that this line is looking the most appropriate line to represent that particular data? Were you able to agree to that? Leave behind variance and all that stuff. Do you think which line is the best representation of this particular data set? Is that this line or some other line?
Yeah, the line, because it touches most of the points. Like points are closer to the line.
Yeah, so this is one of those lines, right? So this is not the best representation of that particular line. None of the points are close to this. And if you want to represent this data using a single line, this will not be that line. That line would be this line. Okay. This is the best representing line for this particular data that we do have. Now understand this intuitively. Now you agreed, you are able to convince yourself that this is the best line that is representing this data, right? Now, do you all able to agree with that? Like saying like this is the best line representing the data, not the other lines we have seen. Okay, so these are different lines that we have seen, but we were able to convince ourselves that this is the line. This is the line which best represents the data. Okay. Now, what principal component will try to do is it will just try to find out such kind of lines. How it will do and all that stuff we will learn later. But what principal component will do is it will try to find out these lines, which we call as principal components. Okay. It will just try to find out these lines. That is its job. So these principal components, what I'm saying is will be equal to number of principal components will be equal to the number of dimensions. Okay. The principal component PCA will try to find out principal components. Principal components are nothing but the lines that we have seen. It will try to find out what it will try to find out. It will try to find out those new lines, and those number of principal components will be equal to the number of dimensions. If we have two dimensions, it will try to find out two principal components, PC1 and PC2. Okay. If it has three dimensions, it finds three principal components, PC1, PC2, PC3. So those principal components are nothing but the lines which best represents the data set. Okay. Then where is dimensionality reduction? It is just finding the number. We have two dimensions. It is finding two principal components. Then where is dimensionality reduction? Where are we actually decreasing the dimensionality? Let's consider in the new space, PC1 principal component is nothing but a linear combination of this data. Can I say it that way? So we have seen a line, right? That line is, can I represent that line as a combination of these two or not? So I have seen this line now. So I have this line, right? I have this particular line, which we thought as the best line or any line. So it's the job of PCA to find out the best line, best fitting line. But just think of this particular line. Can we represent this as a linear combination of these two axes, X and Y? This is a straight line in two-dimensional space, X and Y. Can we represent this line using these two variables? Or these two dimensions, X and Y?
Yes. Yes.
So this is a straight line. So we can represent this line by using these two axes. I can say this as 3x plus 2y or something like that, right? It can be anything. It's just a straight line in two-dimensional space, and that can be represented using these two dimensions. Let's suppose this is x-axis, this is y-axis, and this is what I'm trying to find out, or PCA is trying to find out. Can this be represented as 3x plus 2y, something like that? It all depends upon the slope, right? Slope of this line and something of that sort. So these will comes from the slope of that particular line, right? Do you agree that this line can be represented using in terms of the dimensions, the x and y? Yes or no?
Yes.
So we can represent this line. So now I have two dimensions, which is gene 1 and gene 2. Now I'm trying to find out PC1. So PC1 can be represented as 3 into gene 1 plus 2 into gene 2. Okay, so we are trying to find out the new principal components, which are the linear combination of the original dimensions. That is what PCA is saying. But what is the best fitting line is how PCA finds this best fitting line is what we have to understand. And we also understood that PC1 and PC2 will be the number of principal components will be equal to the number of dimensions. Okay, but how does principal component analysis is doing a dimensional reduction when it is actually trying to find out the same number of principal components? Even now, look at this. Now, if you got some new dimensions, like new components, something like this, you have got. If you ignore about the original dimensions and if you consider these dimensions now, even these are equal to the number of dimensions that we do have. Okay, so let's try to understand how actually principal component analysis is doing a dimensional redirection using principal components. Okay, so that's a different topic. But now what you have to understand is what is a principal component. Principal component is just nothing but a good line that represents the whole data. Okay, those are principal components. And principal components can be represented as a linear combination of the original dimensions. So these are the 2 points that you are trying to actually understand here. Now, the next thing that you have to understand is what are the objectives of principal component analysis. Now, just carefully look at this video, and from this, you will be able to figure out something. Now, what I'm trying to do is my whole target here is to find out the best fitting line for this particular data. Your goal now is to find out the best line that best describes the data points that you do have. Now, what are the parameters that I have to consider here is just carefully observe this. Now, what I'm trying to do is I'm projecting these points onto this new line. Okay, so this is the initial line I started with. I projected these every point. Projection means just drop that point onto that line. So I'm dropping this point onto this line. I'm projecting all the points onto this line. But what is happening, just carefully observe what is happening when when this line is approaching towards the direction of the best line that we have decided in the previous video. Okay, so now as this moves on towards the best direction, you just try to observe what is actually happening to the distances. Okay, so concentrate on the variance. What is variance? Variance is the spread of the data, right? Spread of the data from the mean is called as variance, right? Now, when you projected the points onto this, what is the variance now? Variance is just nothing but this distance, right? From the mean to this. So this describes the variance. The spread from this side to this side, that whole distance describes the variance, right? So once you projected the points onto this, just look at the distance from the center to the distance from the center to the spread of the data. Just look at this video so you'll get some understanding. So now I took some random line. I don't know whether that is a good line or not, but I projected my points onto it. And now what actually happens, just look at what actually happens now. So now the main concentration for us is to find out the variance of the data. So how the variance is changing as the line is approaching towards the best line. You just focus on whether this distance is increasing or not. This is a variance, right? The spread of the data from the mean. This is a variance describer. This line is a variance describer. So how this line is changing, whether that is increasing or decreasing when this red dotted line, which we are trying to find out, that describes the whole data. We are just trying to find out that particular line. Now, what you have to observe is when this line is approaching towards the best fitting line, how this distance is changing. Okay, so I'm just playing that again. So just look at how that distance is changing. So now as the line is moving towards the best fitting line, just look at how that distance is changing. Is that increasing or decreasing when it is approaching towards the best fitting line? Is that increasing or decreasing when it is approaching the best fitting line?
It's increasing.
It is increasing, right? So
Yeah.
what we have to do now to get the best fitting line, we have to maximize the variance, right? This line is an indicator of variance, right? When it is approaching the best fitting line, it is increasing. So that is one of the objectives for us. So when you increase the variance, when you maximize the variance, there is the possibility to get the best fitting line, right?
Yeah.
So when you increase the variance, that ensures that that new component, new principal component captured the most variance in the data. So this line is not capturing the data at all, right? Points are somewhere else and your line is somewhere else. But when you approach that best fitting line, what is happening? When you approach towards that best fitting line, oh, let me just go back. When you approach towards that best fitting line, the variance is getting maximized and you're able to capture the whole data, variance in the data, the spread in the data, right? The spread in the data means how variety the data is. That is what you are trying to capture. So that should be one of our objective to maximize the variance. It should be one of our objectives to find out the best fitting line, right? Do you understood what is the first objective? The goal is to find out that best fitting line. To find out that best fitting line, our objectives is to maximize the variance is our first objective. You also understood why we have to increase the variance or maximize the variance to find out the best fitting line, right? Until unless you find out the or you maximize the variance, you are not getting the best fitting line. So when it is going far away from that particular line, the variance is decreasing. When the line is going far away from these points, which is not covering the whole variance, this distance is increasing. When it is coming close to the points, which is coming close to the best fitting line, the variance is increasing. So you have to maximize the variance. That is the first objective. Is that clear for everyone?
Yes.
Understood to everyone?
Yes.
Yes.
Okay. Now we all know the Pythagoras theorem, right? Now this is the variance for us. Okay. Now we got the variance. So this is the variance. So C is the variance. And when it is coming towards the best line, the variance is increasing. Okay. When it is going far away from that line, the variance is decreasing. I'm taking just one point now to explain you the second objective. Okay. So now this is the dotted line is the best fitting line that we are trying to find out. And when you project this point onto this line, what is that happening? It is forming a right angle triangle, right? So when you have right angle triangle, you have the Pythagoras theorem that says a square is equal to b square plus c square. Okay, so that is what Pythagoras theorem is saying. So for a given point, the distance from the center will never change. This is always constant, right? The distance from center to this point will always be constant, which is a. Now what we are trying to do, we are trying to move this line towards this or far away from this line, right? So we are just moving this point. So we are moving this line towards this point or away from the point to find out the best fitting line. So when it is moving towards this point, C is increasing, right? Right? When this is moving, when this line is moving towards the point, the C is increasing, right? C is nothing but this distance is increasing, right?
Yes, variance.
So when C is increasing, B should decrease, right? Because A is constant. When C is increasing, B will decrease, right? So when this is coming towards this, B will decrease, right? B length will decrease.
Yeah.
So this C, when this C, you know the Pythagoras theorem, right? So when this is A, this is constant. Distance from the center to the point is constant. So this is one kind of rectangle. This is another kind of right angle triangle. So this is also 90 degrees. This is also 90 degrees. But the only thing is here C is more, B is less. Here B is more, C is less. C is less, B is more. C is more, B is less. When C is more, B should be less because the right hand side is constant. Understood? Let's say A is equal to 5. That is constant. Okay. When I take C is equal to 1, what should be the B? Somewhere around 4 dot something something, right?
Yeah.
Yes.
A is constant. When I take C as 4, what should be the B? A should always be constant. Distance from the center.
0.5.
So when C is increasing, B should automatically decrease, right? So that is what its whole thing is. So when C is increasing, B will decrease. When B is increasing, C will decrease. So C has to be increased or decreased to find out the best fitting line. C has to be more or less to find out the best fitting line.
It should be more.
So when we know C has to be more for the best fitting line, what should be the B?
It will be less compared.
Should be low.
Less.
That is what the second objective says. Minimize the sum of when this is maximized. This has to be automatically minimized. So to achieve that objective, you can do either of these things. Either you try to maximize the variance or try to minimize the sum of square distances. I'll come back to sum of square distances, but you can try any of these two things. Okay. You can try to maximize the variance or try to minimize the sum of square distances. Okay. If you do any of these things, you will reach or you will get to your target. Okay. As they both are proportional to each other. As one happens, other will for sure happen. Okay. As C increases, B will for sure decrease. Even if you are trying to decrease B, C will for sure increase. So though that's the reason these two are called as objectives. If you can achieve any one of these to get your ideal principal component or ideal line that covers or that maximizes the variance. Now did you understand what is meant by new directions along which the data has most spread or variance? That is what the variance is. When the variance is more, when the variance covered is more, you will have the best fitting line for that particular data. Okay. So what is sum of square distances? Sum of square distances is nothing but the distance, what you have to minimize, you just have to minimize the distance from the point to the line, right? So this line cannot be the best fitting line. Why? If you're trying to represent all these points with a single line, and if you think this as the fitting line, this cannot be. You're saying this as not a good. I mean, you're saying this as not a good line because this line is far from these points, right? It is somewhere far from these points. An ideal line would be close to these points, right? If you have all the points, if I have single line where all the points will be on that line, then I can say that is the best fitting line for those points, right? So that should be the ideal line. So when you find out an ideal line, what is the case? You have to see the distance from the points to that line should be minimum, right? So the distance from that point has points, the distance of the points to that line should be minimum, right? So that is just basically sum of squared errors means it is just the sum of, this is an error, right? So this is an error because you're trying to represent all the points with a single line, but this is somewhere else. This point is not on the line. So this distance from that line to this point is an error, right? Is that error or not? So there is no error because this is on the line. You're trying to describe these points with the line. This is also on the line. This is also on the line. So this has some error. This is deviating from that line. This is also has some error. It is little far from the line. So you're trying to sum up all these lines, all these errors, x1, x2, x3. This doesn't have any error. This doesn't have any error. You're trying to sum up all these errors. But why you are squaring? You're squaring just because this has an error, right? But it has some different error to this. If you consider this as a positive value, this distance will be negative value, right? So this negative value will cancel this positive error, which we don't want. This is also an error. This is also an error. We don't want this error to cancel this error. When you square this, negative will also, the negative distances will also will become positives. So you will get the right number of right number that you want to measure, and they will not cancel each other. Understood? That's the reason you will actually do a square of these errors. So you square this, square this, square this. Let's suppose if this is -3, this is -2, and this is 1. If you just sum them, it becomes -2 -3 -2 plus 1. So this 1 is contradicting with this, and it is actually decreasing, but we don't want. But if you square them, every error will be contributed 1 square. So negatives will become positive and everything will get contributed. Okay, so that is the idea behind doing a square of sum of squared errors. So this helps to reduce the difference between the original data points and their projections onto the new components, thus retaining accuracy. Okay, is that clear?
Yeah.
Understood?
Yeah.
Yeah.
No, or you understood this? Can I go to the
Yeah,
next?
understood.
Do you want me to explain this again?
Next slide.
Okay, so the main objective of PC is just to find out, use these objectives and solve these objectives. That's all. When you solve these objectives, you will find out those new principal components, and then I'll also show you how that actually brings you to this dimensional detection. So going back to the next slide. Now, as I explained you, PCA works by finding linear combination of the original features that maximize the variance in the data. We already discussed this, right? Let's suppose if I say the slope of this line is 0.25, so that means it extends four paths this way and one part this way. So that becomes the slope of this line, right? So that I can represent this as 4 into gene 1 plus gene 2. The principal component PC1 can be represented as 4 into gene 1 into gene 2. That we already discussed, and you're clear with that, right? And now the next point is just take this as granted for now, and then I'll also show you the proof for that. All principal components are perpendicular to each other. Okay, when you have 3 dimensions and we are trying to find out the principal components for those directions, they all will be perpendicular to each other. Okay, PC1 will be perpendicular to PC2, PC2 will be perpendicular to PC3. Okay, when you find out PC1, when you draw a perpendicular line to that PC1, that becomes PC2. Why they are perpendicular and all, I'll show you the derivation of that and you will slowly understood that. And just understand this, for a symmetric matrix, all the eigenvalues corresponding to distant eigenvalues, all the eigenvectors corresponding to distant eigenvectors are orthogonal to each other. Okay, so if you have a symmetric matrix, all the eigenvalues corresponding to different eigenvector, I mean, all the eigenvectors corresponding to different eigenvalues are perpendicular to each other. Okay, just remember, just take this as granted for now. The first thing I have said is PC1 is perpendicular to all principal components are perpendicular to each other. And for a symmetric matrix, all eigenvectors are perpendicular to each other. Okay, so that is what I was saying to you. Just I'll show you the proof for this shortly, but for now, what your takeaway is, all principal components are parallel to, I mean, perpendicular to each other. Okay, now you got PC1, you calculated PC1, you calculated PC2. Okay, PC2 is nothing but just perpendicular to PC1. And now what I am doing is I'm projecting these points onto both the axes. Okay, projecting the points onto both the axes. If I have this particular point, just give me 1 second. Let me 1 second. Okay, now what I'm trying to do is I'm trying to project all these points onto both the axes. Whatever points that I do have, I'll project the points. Projection is just like dropping the points onto those axes. Okay, that's what I'm trying to do. When I say projection, this point is there, right? I'll just drop this point onto this y-axis, drop this point onto x-axis. Similarly, drop this point onto when I say y-axis, it is PC1 and PC2, the new principal components that I have found. I call this as PC1, the best fitting line that I have found out that covered the most variance in the data or the best described the data. So this is PC1 and this is PC2. Okay, now I'm just projecting every point onto these axes, something like this. Okay, so once they are projected, what I'll do is I'll get rid of the original axis. So this is one of my original axes, right? Gene1, Gene2. I'll get rid of the original axes, and now I'll just keep PC1 and PC2, and I have projected points on the PC1 and PC2. Now what I'll do is I'll just rotate this. So that this becomes the horizontal axis. So now this became my first axis. This became my perpendicular axis to PC1. Now I'll bring back the original points. So earlier we projected, right? Now from the projections, I'll bring the point. So this is the projected, this is the projection. I'll bring back the point. So from the projections, I'll bring the points back again. Okay. So let's suppose this is another point. We do have something of that sort. This point is there. Here is 1.1 point, something like that. Okay. So from the projections, I'll bring the points back again. Now from the Gene1, Gene2 and the points, we have gone to PC1 and PC2, and we were also able to get the points back again. Okay, so that is the transformation we have done. So the main thing over here is finding out the PC1 principal components, right? If you are able to find out the principal components, transforming the points onto those axes is just an easy job. Okay, the main goal here is to find out the principal components. Now have you got an understanding of how we transform from the original dimensionality space to principal component space? Hello.
Yeah, got it.
Yeah. Now, what we do as the next step is, this is an important thing that helps you how PCI will actually do the dimensionality reduction. Okay. Now, okay. Let's say this. Okay. Scree plot is nothing but the variances plot, which is PC1 and PC2. Let's not bother about these numbers 83 and 17. I'll come back to this again, but just take them as an example. Let's suppose if principal one component PC1 has covered 83% of the information in the data, or I'll say variance in the data. PC2 component has 17% variance in the data. Okay, what does that means? So this data, look at this data, the spread of the data along x-axis is 83%. They are mostly spread along this PC1. Spread along y is just 17, very little, right? The spread along this PC2 is very less. Spread along PC1 is more when you look at the data, right? So that is what we are plotting. The variance along PC1 and variance along PC2 is what we are plotting. Okay. So that is what scree plot means. And if you're taking three-dimensional data set, and now we got three principal components, PC1, PC2, PC3, and we are projecting the points onto the principal component, principal components PC1, PC2, and PC3. So here is the takeaway. Now we have three-dimensional points, right? We got three principal components. And what this says, 79% of the variance is in the first principal component. 15% of the variance is in the second principal component. Principal component 3 has just 6% of variance. Now it is given that it's a value given to it. Just make sure you capture 90% of the variance in your data. Okay, so you do a dimensionality reduction but capture 90% of the variance in the data. Then what you're going to do is so now calculate the percentage of variance. In PC1 you have 79%, in PC2 you have 15%, which totals to 94%, right? So you don't need the third dimension because your goal is just to find out 90% of variance in the data. So then what happens is, now in a three dimension you project points onto every dimension, right? 1, 2, 3. As I don't want the third dimension, I'll just ignore the third dimension, and now I'll just take PC1 and PC2 and project the points back on this, in this space, PC1 and PC2. Okay, so I'll get the points from these projections from PC1 and PC2. So that is how principal component analysis will do a dimensionality reduction. So we calculates the variance covered by each principal component. Let's suppose I have four principal components, PC1, PC2, PC3, and PC4. This covered 10, 20, 30, 40. Okay, so now it is said that capture 70% of variance in the data. If you are okay to capture just 70% of variance in the data and reduce the dimensional and do a dimensional reduction, you can get rid of these two dimensions. So when you're actually calculating the principal components, what you're doing, you're individually separating each principal component. So what you're doing, once the principal components came up, you're projecting the point onto every dimension, right? You're projecting the point onto every dimension, and then combining them again in the new dimensional space. Now if you have four such dimensions, you're projecting the points onto all the four dimensions. Now if you want to get rid of two dimensions, just get rid of these two dimensions and create a space only with the remaining principal components and bring the projections back to form the points. Okay, so now here my requirement, here I'm okay to have just 70% of variance in the data. So I'll just go with two principal components. I have projections already on those points. So what I'll just do is bring those points back from these two dimensions, something like this. Okay, now I got rid of these two dimensions, the other two dimensions. Now I created an two-dimensional space from four-dimensional space. If my requirement says I'm okay to have, I must have 90% of variance, then I should take three principal components. I should have 100% of variance, then there is no other way. You just have to take four dimensions. So depending on the percentage of variance that you're okay with, you will actually reduce the dimensionalities. And it is completely feasible to reduce the dimensionality just by, going back, removing those principal components and projecting the, or getting the points back from the projections. Is that clear how it actually is reducing the dimensions in PCA? Understood?
Yeah.
Now don't bother about the calculations. This 79% is how PC1 is getting 79%, 83%, and all this stuff. We'll actually come back to this shortly. And but when you know these values, and you know the requirement, if you're okay to have just 90% of variance in the data, And if you are okay to lose the rest of the information, which is not more valuable, so you can just do a dimensional reduction this way. Just come up with new principal components, project the points back. I mean, get the points back from the projections on each dimension. Okay, so this is all what principal component analysis will do to get the new dimensions out from the existing dimensions. Now this is the real mathematics. I mean, we use all the things that we have learned, maximum, minimum, and all that stuff. So what we are trying to do, we are trying to maximize the variance, right? So so this is just an intuition for it. So here we have some variance. I'll do a graph for this. Here we have some variance. Let's suppose some x, some 2 variance is there. As the line is slowly moving towards this, the variance is increasing. At some point we have maximum variance. Okay, when it actually covered the whole data set, we will get a variance. And if you still move the line forward, what happens? Variance again decreases. Okay, variance decreases, it reaches to the low again. So now what you're trying to find out, we are trying to find out the maximum variance, right? So that is what we are trying to do here. So when you keep on rotating this line, this line is from this variance to it is growing to this variance at some point, and then again it is decreasing. So we are interested in this point. That is where you will get your PC1, or the direction which will have the maximum variance. Okay, that maximum point we are trying to find out. That's the reason we learned about finding the maximums and minimums. Okay, now let's come back to the intuition and apply these concepts that we have learned. So I'll come back from 1D space, okay, or else yeah, I'll start it this way. Okay, the first thing that you have to do is, so now with this what you will learn is how to actually get those principal components, how to get the linear combination data and all that stuff. That is what you are going to learn in just few minutes. Okay, so I'll start with this example. That example is this one. Are you able to understand everything till this point?
Yeah.
Now I'm going to start it this way. Okay, what I'm trying to do here is, so much stuff. Okay. Right. So let me start with this. I'll take a simple dimensionality data set. Okay. What I'm trying to do here is colors to on. So I have taken some points like this. Okay. You can consider that as one dimension also, that is fine. Okay. These are my different points. Now, what I'm trying to find out, I'm trying to, in two-dimensional space, I tried to find out the best fitting line for the points, right? In 2D space, it is a line that best fits the points. But in 1D space, what is the point that best represents the data? What is the best point representation of this data? If I have some data like this, what is the best representing point of this data? Is that not the mean?
Mean, yeah, mean.
So mean is the best representation of this data. So when you know the mean is the best representation of the data, this should have the minimum sum of squared errors, right? From every other point. Is that right? So we told that we just discussed in the last slide that sum of square distances will be minimized or will be minimum for the best fitting line, right? So for the best fitting point, sum of squared errors will be minimum, right? What is the sum of squared errors? Sum of squared errors is nothing but distance from the mean to every point, right? Xi minus m whole square. Is this what sum of squared distances means? From mean to every other point, from sigma I is equal to 1 to n. So I'm trying to calculate the distance from every point to the mean. That is xi minus m whole square. This is x2, x1, x2 minus m whole square, x3 minus m, x2, 4 minus m. So I'm doing a summation of all the distances from that point to this point. Is this clear or not? So in a one-dimensional space, how do we represent a point? Like 2, or if it's an x-axis 2, 0, 3, 0, 4, 0, and if I say the mean is 1, 0, if I say the mean of this is, I'll say the mean is 1, 0. How do we calculate the distance? 2 minus 1 whole square, 4 minus 1 whole square, 3 minus 1 whole square, right? y2 minus y1 will always be equal to 0. So this becomes 2 minus 1 whole square plus 4 minus 1 whole square plus 3 minus 1 whole square. Something like this, right? That's what the sum of square distances from every point. What is the distance formula? x2 minus x1 whole square plus y2 minus y0 whole square, right? Root over square distances. We'll just get rid of the square. I mean, get rid of the root. Are you getting this? Hello?
Yeah, that's
Yeah. So this is the sum of square distances. Now what we have to do when you have to minimize this. Okay. So you are trying to minimize the variance, the sum of square distances. When it is variance, you have to maximize it. So when you're trying to minimize the sum of square distances, or so how do you actually get this sum of square distances? This is the sum of square distances. So now what I'll do is I need to differentiate this, right, with respect to the mean m. So when I differentiate this with respect to m, just see what I'm getting. So this becomes minus 2 into xi minus m into minus 1, right? So that becomes 2 into xi minus m. And this is from I is equal to 1 to n. Is it right? So I need to equate this to 0. Okay. And now what this becomes? 2, if I go, if 2 goes this side, that will be equal to 0. So this becomes sigma I is equal to 1 to n xi minus m is equal to 0. Okay. So I'm breaking this into two different things. I is equal to 1 to n xi minus sigma I is equal to 1 to n m, that is equal to 0. So that becomes, so this becomes sigma I is equal to 1 to n m is equal to sigma I is equal to 1 to n xi. Okay. So m is a constant value, xi is a variable. So I'm taking m outside. Sigma I is equal to 1 to n is nothing but 1 plus 1 plus 1 plus so on up to n, right? So that becomes n into m, right? Is equal to sigma I is equal to 1 to n xi. So m becomes 1 by n sigma I is equal to 1 to n xi. Okay, is this not the mean? Mean is sum of the points by number of points, right? So what happened? When you take one-dimensional data, we got that mean is the best representation of those points. You just have done minimized. You minimized the sum of square distances. What you have done, you take a derivative and equated that to 0, and you got the value of m. So what you just have to do when you want to know whether this is minimum or maximum, just have to go do a second derivative. So that says that is the minimum value or the maximum value. So how do you do the second derivative for this with respect to m? How do you take the second derivative for this? You're going to take the second derivative with respect to m. So this becomes constant, it becomes 0, and you get -1. So when you get less than 0,
It is maximum. Local maximum.
Local maximum.
so we are trying to minimize this sum of square distances. What is our first derivative? First derivative is 2 into xi minus m into -1. So that becomes -2, right? So what is the first derivative? First derivative is, I'm doing the first derivative of value here, -2 into sigma I is equal to 1 to n xi minus m, right? That is our first derivative. When you do the second derivative, it becomes -2 into sigma I is equal to 1 to n minus 1, right? So that becomes +2, which is greater than 0. So at this value, we are minimizing the sum of square distances. So this is completely wrong. There is -2 before this.
Okay.
Right? So the first derivative is 2 into xi minus m into -1. So that becomes -2 sigma I is equal to 1 xi minus m. And then if you take the derivative again, double derivative, this becomes -2 sigma I is equal to 1, xi is constant, minus m will become -1. So -1 into -2 will become +2. Sigma I is equal to 1 to n will become 2n. So 2n is always greater than 0. So when it is greater than 0, at this particular m, we are getting the minimum value for the sum of squared errors. So when you minimize the sum of squared errors, that is becoming the mean. So mean is the point which minimizes the sum of square distances from different points in 1D space. Understood?
Yeah.
Yeah, we just made a wrong calculation here. It is not, here we're getting -1, but we have -2 before. So -2 into -1 will become +2. So that's where the confusion happened. You have to write it better. So that is a 2D case. From this, what you have understood in 1D, I mean, in 1D case, mean is the best representation for the points. Okay. Now we go back to the 2D dimension and try to find out let's try to maximize the variance. Here we have minimized the sum of square distances. Obviously, what it will do, it will maximize the variance, right? They are proportional to each other. Now try in 2D case, let's try with the other one, which is maximizing the variance. Okay. Now, what I want to do is we will try to maximize the variance at the points in 2D space. Okay. Let's take this example again. We all know what is the formula of the variance. Variance is written as 1 by n sigma I is equal to 1 to n x minus mu whole square. So this is the formula for the variance, right? Is that right?
Yeah.
So this is the formula for the variance. Now what we are trying to find out here, so we have seen that this is our gene 1, gene 2, and this is the line which we are trying to find out. Okay. So basically we are just bothered about this distance from the origin to this particular point, right? It's just like double or something. It's just a multiplication factor, but this basically we are trying to find out the distance from the center to this one. So that is what it is increasing, right? Distance from this point. The variance means spread of the data. The spread of the data will also applies to this side, but it is just a factor of this. So if this is D, this would be approximate to 2D, right? Something like double. But let's concentrate. Let's not go to 2D. Just try to concentrate this for one point. The distance from the center to that one point, that gives us the variance. This t, when we moving to the best line, this t is increasing, so this t we are trying to maximize. Okay, now what we are doing, we are projecting the point onto this, right? We are projecting every point onto this pc1, or the line to which we are trying to find out. We are projecting the points, right? We are not just keeping the points there. How we are calculating the distance, that variance is nothing but how far the data spread from the mean. That is what we are trying to find out, correct? So let me put it this way. This is the final derivation, and this says you everything, which is very important to understand every step. So let me make it so clear. So what I am trying to do here is, this is my real axes, and now I have a point. Let's focus on only one point. Okay, so I have multiple points like this. We have seen different points like this. Now what I'm trying to find out, I'm trying to find out a new line. Okay, what that new line looks like, how that new line actually looks like, it looks like this. Okay, this is the new line which I'm trying to find out. And then what I'm trying to do, I'm projecting these points onto that line. Okay, I'm projecting these points onto that particular line. Okay, I'm projecting these points onto that particular line. I'm projecting every point here onto this line. So variance, this is, this is mean, because we shifted all the points. So we standardized all the points so that the mean falls at 0, 0. And now we are trying to find out this distance, right? This is t that we have seen in that video. And when it is approaching the best line, the d is increasing. I mean, we are maximizing the variance, right? So when the line is approaching towards the best line, the d is increasing. The variance is actually increasing. This d is increasing, right? Agreed? So we are just trying to maximize this d. The d is nothing but the projected point, the distance from the mean to the projected point. Is that right? D is not, what is d? D is the distance from the mean to the projected point. So when you calculate variance, for every point, you will actually calculate that and do a summation on all that. So what are the points here? Points are nothing but the projected points of this on this particular point. Okay, this to this. That is what projection actually means is. Okay, D is nothing but the distance from mean to the projected point. Okay, because we project all the points onto this particular line, right? And we want to maximize that. So what that is calculated by the variance. This is the formula for calculating all that variance. So X is nothing but the projected points of the original data set. Okay, mu is also the projected mean on this axis, even though it is 0. In general case, if that is not 0, that is the projected point on the PC1. Okay, so is this clear till this point? Hello.
Yeah.
You all remember how do we calculate a variance, right? So we have multiple points, and if we have mu given as 2, and we have two different points 1, 2, 3, 4, 5, 6. What we have done, 1 minus 2 whole square plus 2 minus 2 whole square plus 3 minus 2 whole square plus 6 minus 2 whole square. Is this not what we have done when you are trying to find out the variance using the
Yes.
now what is this point? This point is nothing but this projection of this point. Projection, finding out what is this point is not your deal. Okay, finding out the projected point is not something. If this point is given as 1 comma 2, what is this point will become, what is the projected point will become, is not what you're trying to find out here. But just try to understand, if a point is projected here, when you're trying to calculate the variance, you are just trying to calculate the variance from this. If this is the mu, this is x1, this is x bar, let's say you're trying to find out the variance for all these points. Okay, that is just a simple calculation, and you're trying to maximize this variance, because maximizing the variance will give you the best fitting line for the points in your data set, right?
Yes.
Is that not clear still? You're just trying to find out the variance to the projected points, and that variance is increasing when it is approaching towards the best fitting line. So when you calculate the variance, the formula is given as 1 by n sigma is equal to 1 xi minus mu whole square. Now what does xi will become? Xi will be the projected point of the main point. Xi is the original point. Now we are trying to find out the variance to the projected point. So I'll replace x with x cap. X cap is nothing but the projected point of this point. If I say this is x, this will be x cap. Okay, so this is the original point and this is the projected point, minus mu will become mu cap. Mu will also be the projected point. If mu is somewhere else, if I projecting onto this PC1, that becomes mu cap. Okay, and I'll say the angle of this principal component is u1. You will just, this is the vector of the principal component. Vector is something like which will have magnitude and the direction, right? So you will just keep changing this u1, the vector direction, so that you will get the best fitting principal component. Okay, so that is, this is u1 and you change the angle, this is the new u1, something like that. Now you have to understand how do we get the projected point onto a particular line. Okay, let's suppose I am given like this. I have a point x. I want to get the value of this x onto vector. I want to project this point x onto vector u1. So how do the formula for this is x dot u1 by u1 into u1 and u1 cap. u1 is the direction and the magnitude of that point will become this one, x multiplied with u1 cap by u1 dot u1. Okay, let me just give you one simple example so that you will understand that. Okay, so I want to find out, just understand the projection for now. We have a point 1 comma 2. We want to project this onto 6 comma 8, a vector 6i plus 8j. Okay, if you want to project this onto this, what you have to do is, it is as simple as this. As I told you, this is x and this is u. If I have to get this point on this vector, I have to do a dot product. 6 into 1, 6 plus 8 into 16, 16 by modulus of u into u. That becomes, what does u into u will become? 6 into 6 plus 8 into 8. So u dot u, what does u dot u means? 6i plus 8j dot 6i plus 8j. What does that become? 6 into 6, I dot j will be 0, j dot I will be 0, plus 8 into 8. And u cap. U cap is nothing but 6i plus 8j. Okay. So what does this become? 6 plus 16? 22, right? By 36 plus 64, 100. 100 into 6i plus 8j. Right? So when you multiply this becomes 132 by 100. And the I plus 22 into 8. What does that become? 178, right? 176. 176 by 100 and j. So this is the projected point. If you take this projected point on that line is 1.32 comma 1.76. So that is the projected point. That is the projected point of x. This is the original point. This is the projected point on this vector. Understood? So that is what basically, how do we calculate the projected point? Even if you draw this, you will clearly understand that. Like, if you just scale this in the right way, 1, 2, let me just go back and add a new slide. So just so now what we have got this, right? On 1 comma 2, so the point 1 comma 2 has become 6 comma 38. So the point 1 comma 2 projected onto 6i plus 8j vector did became 1.32 comma 1.76. That is the projection of 1.2 on 6 comma 8. So you can just draw this and to understand this. So what does that means is, this is 1, 2, 3, 4, 5, 6, 7, 8. This is 1, 2, 3, 4, 5, 6, 7, and 8. So the given point here is 1 comma 2. Okay. What is the given point here? Is 1 comma 2. The given point here is 1 comma 2. So this is the given point. And what is the vector that is given? 6 comma 8. So this is the vector given. So this is the vector, and you are trying to project this point onto this particular line. So this is 1 comma 2. This became 1.32 comma 1.7. So does this make sense? So this is 1, and the projection is somewhere here, which is more between 1 and 2. So this become 1.32. And this is 2, and it is the y-axis is less than 2, 1.76. So that is the projection of a point onto this particular vector. Y-z vector, it has direction and also this one. So that is how you calculate the projection. Understood now? So now you understood that the projection of a point onto a vector is equal to so you understood this. What is the projection of a point onto a vector? Projection of a point onto a vector u. Projection of a point onto a vector u is equal to x dot u by u dot u and u cap is the direction of that component. So this is the magnitude and this is the direction of the new projected point. Is that clear? Hello? Understood or not?
Yes.
Not clear or what? Yeah, it's just the projection. When you want to find out the projection of a particular point onto any of the vectors, or you just have to use this formula x dot u by u dot u into u cap. So that actually gives you the projection of the point onto this vector. So what we are trying to find out here, we are trying to find out the variance. Variance is from the mean to the projected points. So x cap is the projected point of x. Mu cap is the projected mean of all the points. So this is x. I am projecting this to x cap, and the x I'm trying to project to a vector called as u1. U1 I'm naming the principal component as u1 here. Okay. So now it all comes down to this. What it all comes down to right now is we are trying to maximize. We are just trying to maximize this particular formula now. What is that formula? Variance is equal to we are trying to maximize variance is equal to what is the variance formula that we have got now? We are trying to maximize the variance. The variance is given by 1 by n sigma I is equal to 1 to n x cap minus mu cap whole square, right? That is what we are trying to maximize from the projected mean to the from the projected point to the mean. X cap is the projected point, mu cap is the projected mean. Now principal vector is given as u1, right? Now let's say x cap is equal to point x. We are trying to project point x onto vector u1 by u1 dot u1 into u cap, right? So here there is a constraint for us. The constraint is, let's consider u1 as unit vector. That means u1 dot u1 is equal to 1. Okay. If you want to change this to matrix form, this becomes u transpose into u is equal to 1. So that is the matrix denotion of a vector. Okay. That is a matrix denotion of an vector, u transpose into u. Okay. Or this is u1 transpose into u1. So if you don't understand these two things, let me just do a dot product and for two vectors and let me show you. So I'm taking a vector u as 2 comma 3, that is 2i plus 3j. So if I do a dot product between these two, what I'll get? 2i plus 3j into dot product of 2i plus 3j. That becomes 4 plus 9. That becomes 13. Yeah, now if I want to represent this in matrix form, this vector, this is u, right? This is the cardinal form of a vector. Now I have to take the u transpose into u. What does u transpose become? 2 comma 3 and u is 2 3. This is the transpose, this is the vector. Now let's multiply this. 2 into 2 plus 3 into 3, which is 13, right? So this is you're trying to do u transpose into u. Here you have done u dot u. So u dot u gave 13, u transpose into u is given 13. So this u dot u can be represented in matrix form as u1 transpose into u1. So this is the constraint. So what I'm saying is I'm considering now u1 as unit vector. So constraint is restricting the values of u1. Now what we are trying to do with u1? U1, we are trying to find out the direction of the U1. That is our main goal. When you maximize the variance, you are expecting that you're trying to find out the direction of U1, right? That is your goal. So, but you're saying that u1, you are restricting the u1 with some condition, that is u1 transpose into u1. So when you have a constraint, what you have to do, you have to use Lagrange and multiplier if you want to find out the maximum value. So that's what it all comes down to. So now I represented u1 dot u1 as u1 transpose into u1, and let's go forward and find out the maximum values now. Let's maximize this. This gives you the whole intuition behind the principal component analysis. Okay, so how do we calculate the principal components and all this stuff? So once this is done, you will get you'll get to know, or you will be able to accept a few things. Now I know the projection is done. Now I know u1 dot u1 is equal to 1, so I can write x cap as, how can I write x cap now? I can write x cap as x dot mu1, right? Because u1 dot u1 is equal to 1, that is a constant, we will solve that later. Now I'll come back here, I'll apply the same thing here. 1 by n sigma I is equal to 1 to n. I'm replacing x cap with x dot u1. Okay, minus I am applying u cap. Similarly, mu cap is nothing but original mu into mu1, right? So I am applying mu dot mu1 whole square. Okay, so that is what we have actually done now. Okay, now what I'll do is I'll do a transform. I'll represent this in matrix form now. So that becomes 1 by n into sigma I is equal to 1 to n u1 transpose into x minus u1 transpose into mu, which is mu whole square. Because anything u1 dot u1 can be represented as u1 transpose into u1. Now I have represented x dot mu1 as mu1 transpose into x, mu dot mu1 as mu1 transpose into x. It can be represented as mu transpose into mu. It can also be represented as mu transpose into mu1, x transpose into mu1. That is also fine. This is also fine. Anyways, it will work out. So I am just making u1 as common. u1 transpose into x minus u1 transpose into x. So what I'll do next is I'll take the u1 transpose outside. I is equal to 1 to n mu1 transpose into x minus mu whole square. I'll take this. Okay. So now this is what I do have, right? So this can be written like this. So this square, I'm converting this square into multiple matrices. Just observe this denotation. This is the major important thing. Now I'm converting this to this way. 1 by n sigma I is equal to 1 to n mu1 transpose xi minus mu into xi minus mu whole transpose into mu. So mu1 transpose whole square is nothing but can be written as mu1 transpose into mu, right? That is matrix multiplication. Mu1 transpose into mu is nothing but mu square. Xi minus mu whole square is nothing but xi minus mu whole transpose into xi minus mu. Okay. What can be written as x square in matrix notation is nothing but x transpose into x. That is what I have done here. Mu1, I mean, this is u1, right? Sorry, this is u1. u1 transpose. So that becomes u1 u transpose minus, okay. This is u1, not mu. So the inside you have mu and the outside you have u. Okay. So this become u transpose xi minus mu into xi minus mu whole transpose into u. U or u1. You have taken u1, right? Anything is fine. So let's suppose that as u1 or u, whatever it is. Okay. So just carefully observe now. This is where the whole point comes down to. Okay. So that becomes u. Now I'm just rearranging the items here. So that is u transpose 1 by n sigma I is equal to 1 to n xi minus mu into xi minus mu whole transpose into u. Okay. Now, if you carefully observe this, term, if you carefully observe this term, can we say this as sigma covariance matrix? Xi minus mu into Xi minus mu whole transpose. Can we say this as covariance matrix? Yes or no? Okay, let's try to derive the covariance matrix first, and then let's come back here. So I'm trying to do the covariance matrix. I'm trying to represent that as covariance matrix now. How can I prove that as a covariance matrix? So coming back to this again, we know what is covariance matrix, right? What is covariance matrix? How do you represent the covariance matrix? Covariance matrix can be represented as this one, right? Sigma x square, sigma xy, sigma yx, sigma y square. Okay, this is what this is how we can actually represent a matrix, right? Covariance matrix. Is that right? Hello.
Yeah.
Right. Now look at just this thing. What I'm trying to do is, given a matrix, I was given a matrix X. X is nothing but x1, x2, y1, y2. Okay, I'm just taking a simple matrix. Now I'll calculate the mu of this. Okay, mean of this matrix. Now what I'm trying to do is x minus mu. I'll do x minus mu, that is equal to xi minus mu x, x2 minus mu x. Similarly, yi minus mu y, y2 minus mu y. Okay, this is x minus mu, right? Now what I am trying to do is x minus mu whole transpose into x minus mu. This is what I'm trying to do now. Okay, so what is this coming down to? Xi minus mu x, yi minus mu y, x2 minus mu x, y2 minus mu y. So this is the transpose matrix, right? Right, the transpose of this matrix is this or not? Rows will become columns. And the xi minus mu will be xi minus mu x. That would be the same, x2 minus mu x. yi minus mu y, y2 minus mu y. Right? So this is x minus mu whole transpose, and this is x minus mu. Now if we do this matrix multiplication, what are we getting? This has to be this one. This has to be multiplied with this, right? So just observe what you're getting right now. So this becomes xi minus mu x whole square plus x2 minus mu x whole square. Right, that is what you're getting. When you multiply this with this row will become xi minus mu x, yi minus mu y plus x2 minus mu x plus y2 minus mu y, right? And if you multiply this with this, what it is coming down to? yi minus mu y into xi minus x1 minus mu x plus y2 minus mu y into x2 minus, y2 minus mu y into x2 minus mu x, right? And the last one is yi minus mu y whole square plus y2 minus mu y whole square. Okay, now Is this not sigma x square? Is this not sigma xy? Is this not sigma yx? Is this not sigma y square? Just you can just add one by on both sides if you has to be more precise. Just denominators will not do anything much. So now can we write this is sigma, which is covariance matrix. Can we write sigma as 1 by n sigma x minus mu whole transpose and x minus mu? Can we write?
Yeah.
Right. So now that's what I have written. Now this is what we have derived now. So this can be written as U transpose sigma into mu. Okay. So this is what the representation of the variance now. U transpose sigma U. Now we have a constraint. What is that constraint? U transpose into U is a constraint. U1 or U, whatever it is. Now if I have to write the Lagrangian equation, how do I write the Lagrangian equation now? You have a constraint and you want to construct the Lagrangian equation. So to write the Lagrange's equation, what you just have to do is U transpose sigma U minus lambda into U transpose U minus 1. That is what we have seen, right? Lagrangian multipliers. You remember that? We have seen the Lagrangian multiplier, right? What is that?
Yeah.
It's plus.
Out of
Plus or minus whatever it is, it doesn't really matter any much. So that's what we have. We were trying to do here. So going back here. Okay. So you can also even put this as plus. That doesn't really matter. Now this is our Lagrangian equation. What are the variables here? U, sigma, and lambda, right? Now derive this lambda with every variable. Sigma lambda by sigma u. What does that will become? 2 sigma u. U transpose into u is nothing but u square. That was what the matrix representation, and u transpose u can be written as u square plus lambda into u transpose into u will be again become 2u. Okay, and minus lambda will become 0 with respect to this. So what does this will become? Sigma u plus lambda u into 2. We have to equate this to 0, right? The first derivative should be equated to 0 to get the values of anything. So if I equate this to 0, this becomes sigma u plus lambda u is equal to 0. So sigma u is equal to minus lambda u. Okay. So if you look at this, are you remembering, are you able to get something? Are you able to remember anything from eigenvectors, eigenvalues? How do we find the eigenvectors for a given matrix A? You have seen that, right? Ax is equal to lambda x, and lambda is eigenvalue. X is eigenvector, A is the matrix.
yeah.
That is how you find out the eigenvectors, right? And how do you find the eigenvalues?
Determinant of A minus lambda equals.
Determinant of A minus lambda I, right? That's how you find out the eigenvalues. Okay, so this is a Lagrangian constant. So you can just add minus here, not specifically plus. So this becomes plus, which exactly matches the eigenvalue equations. Now from this, can you say u is what you're trying to find out, right? Okay. What is your goal when you're trying to do this? You want to find out the u, okay? And you want to maximize the variance. When you're trying to maximize the variance and you have solved this equation and you got this equation from this, you got that lambda is eigenvalue, sigma is the matrix, u is the eigenvector of that matrix, right? U is, what is u? U is the eigenvector of that matrix, right? A. What is x? X is the eigenvector of matrix A or not?
Yes.
So u is an eigenvector of sigma or not?
Mm.
So now, if you find the eigenvectors of this covariance matrix, can we say we get the principal components of that matrix of the principal component axes? This is the statement. If we find the eigenvectors of covariance matrix, we get the principal components, is what I'm saying. From this, will you be able to agree that or not?
Yes.
Now you know u is the eigenvector of covariance matrix. You want to maximize this. When you want to maximize an eigenvector, what value decides the magnitude of an eigenvector or the length of an eigenvector? Is that not eigenvalue? You remember eigenvalue is just what it says the length of the eigenvector. You stretch it or extend it. We took the example of a rubber, saying like the eigenvalue decides the negative the negative of eigenvalue decides the eigenvector is shrinking, and the eigenvalue is more, the eigenvector is expanding. That's what we have learned. You remember that?
Yeah.
So now you know you can get the eigenvectors when you calculate the eigenvectors of the covariance matrix. You are getting the principal components. Principal components are just nothing but the eigenvectors. To get these to maximize these eigenvectors, what you have to do, you have to choose the highest eigenvalue. When you choose more eigenvalue, the eigenvector will be more. When you choose less eigenvalue, the eigenvalue will be less. Understood?
Yeah.
So that is what PCA is. What PCA, your main goal with PCA is you have to find out the principal components. Now to find out the principal components, you have to find out the eigenvectors of covariance matrix. So once the eigenvectors of covariance matrix are found, the principal components has to be maximized. So the eigenvector associated with the largest eigenvalue will become the first principal component because it carries the most variance. Okay, most variance, the length of the eigenvector will be more when the lambda and the eigenvalue will be more, right? So the first eigenvalue will carry the most variance in the data, and the next highest eigenvalue will be the PC2. The next eigenvalue will be PC3. Now this is the intuition for you now. Now the conclusion is this. You got sigma. When you calculate the eigenvectors of this, you'll get principal components, and the associated lambdas, if arranged in the descending orders, the first eigenvalue associated eigenvector will be the PC1. Okay. The second eigenvalue associated eigenvector will be PC2 because you're trying to find the maximum variance in the data. Maximum variance in the data is nothing but maximum stretch in the eigenvector. Maximum stretch in the eigenvector will happen when eigenvalue is more. Okay, so you arrange all the eigenvectors. Let's suppose my eigenvalues for my matrix is 8, 2 and 1. Okay, these are my eigenvalues. So the total variance in the data is 100%. If I say the variance carried by the first eigenvector is nothing but, how much would be that? It is nothing but 8 by 8 plus 2 plus 1. That is 8 by 11 into 100. So 800 by 11, how much it would be?
Around 70.
Percentage of the variance will be carried by this principal component 1. What is the percentage of variance carried by this? 200 divided by 11, which is 18% by the second principal component. What is the first principal component? It would be 9%, right? So this is how you calculate the variances carried by each principal component. Now it makes sense to you, right? 79% by the first principal component, 15% by the second principal component, third percentage, 6% by the principal component. These are nothing but proportional to the eigenvalues of the covariance matrix. And when you represent this in graphical form, that becomes the skew plot. Okay. Now, if you say you just want only, 90% of the variance covered, you can just take first two principal components or first two eigenvectors. Okay. So this is all about, principal component analysis, and it all comes down to covariance matrix. That is what we are trying to find out now. Now as we know all that stuff, just try to understand. Again, I'm saying this is all the intuition understanding and the in-depth understanding of principal component analysis. So how the principal component analysis will actually be applied, so that whenever in future you're getting some data, you can directly apply this. But it all comes down to only one line when you do the coding. Okay, you don't calculate covariance matrices or eigenvectors. You won't do all that stuff. It is just a single line. PCA component and component is equal to 2 is what you write in Python code. That will actually do the dimensional reduction for you. It's a single line, but we are almost discussing it for 3 months because it has a purpose to discuss. You should understand how that is happening, or else you will be blind in understanding that what are the eigenvectors. When you say principal components, they are the eigenvectors is what you have to understand. If that is not, you cannot do analysis. So now we are simplifying the stuff. Now given a matrix, so just see how we are actually calculating the principal components now, how we are combining the original accesses to principal components. So given a matrix with 3 samples and 2 features, so these are dimensions. Features are also always dimensions. Now we are given 2 dimensions and 3 points. Okay, so feature 1, 2, 4, 6, 1, 3, 5. Okay, so this is the data set. Next, what you have to do, you have to standardize the data set. Standardizing in the sense, find the mean and subtract the mean. So you moved the points from this space to, you move the points from this space to this space. So the mean becomes 0, and you moved all the points from that space to this space. Now we found out the centered data. And then what you have to get the principal components, what you have to do it, you have to get the eigenvectors and eigenvalues of the covariance matrix, right? So to get the covariance matrix, you have to calculate the covariance matrix. And you know the formula for the covariance matrix, right? From the X, I already shown you the proof. X transpose X centered. So this is our new matrix, centered matrix. From that, we will calculate the covariance matrix by just multiplying the transpose with X. So now you got the covariance matrix, and then you calculate the eigenvalues and eigenvectors. Eigenvalues, once you calculate the eigenvalues, so these are the eigenvalues for you now, 8, 0. Now, these are the eigenvectors, v1, v2. Okay, so now we got the eigenvectors and eigenvalues. Now tell me, what is the variance carried by the first principal component? What is the variance, um, you know, present in first principal component? Hello. It is 100% right? 8 by 8 plus 0, which is 100% variance is in the first principal component and 0% variance in the second component. Now we got two dimensions, two features, right? So these are the corresponding eigenvectors. Now the first principal component will be represented as 1 into feature 1 plus 1 into feature 2. So that is a linear combination of feature, the main dimensions, and this is a new principal component. Principal component 2 is written as 1 in minus 1 into feature 1 plus 1 into feature 2. So that is how we actually represent when you get the eigenvectors. This 1 will be multiplied with the first principal component and the 2 will be multiplied by the second feature, second dimension. So minus 1 into feature 1 plus 1 into feature 2. That is the linear combination of the data. And now you got, PC1 is the angle, right, on which you have all the points. Now you want to project the points, the original points, onto this vector, okay, onto this dimension. You have to project the points. To project the points, you can just multiply the matrices. Okay, when it is in vector form, you have to do that x into u by u1 to u and all that stuff. When it is in matrix form, you can just multiply. Matrix notation is just a rotation is what you have, right? Matrix transformation is just nothing but the rotation. So now you take this eigenvector, because why you are taking only one eigenvector, all the variance is in the only one, all the variance in the data is present only in the first principal component. So you can ignore the principal component, so that you are reducing from 2 dimensions to 1 dimension. So now the new points will become minus 4, 0 and 1. On this new principal component, the points will become 0, 4, minus 4. So we reduced the data from 2-dimensional space to 1-dimensional space. Okay, so if you represent these dots in on a scale, let me take this one. So what I'm trying to do is here is I'm representing these points on a scale. How do they look like is color is red. So this is 1, 2, 3, 4, 5 and 6. This is 1, 2, 3, 4 and 5. Okay, so 2, 1, this is 1 point. 4, 6. So 4, 3, sorry. 4, 3 is 1 point. 6, 5 is another point. So now we got a new dimension, something like this. So this became 0, this became 4, this became minus 4. Okay, even if you calculate the distance between these 2 points, what is the distance between these 2 points? So this is 4, 3, right? 4, 3 is 1 point. 2, 1 is 1 point. What is the distance between these 2 points? x2 minus x1 whole square plus y2 minus y1 whole square, square root of this. So this become root 8.
Root
2 root 2, right? This become 2 root 2. 6, 5, 2 root 2. In the new dimensional space, the distance between them became 4. Equal distance. Basically, the distance from, even if you look at the distance, this became 2 root 2, right? This distance is also 2 root 2. Right? 6, 5 to 4, 3. What is the distance? It is the same, right? 2 root 2 only. So the distance from from this point to this point is same, this point to this point is same. In the new dimension also, this point to this point is same, this point to this point to this point is same. So we will not, the distance still remain the same. Okay. So just look at this thing. So we're combining the features, right? So this is the new coordinate system in the PC1. So let's see if you're getting these points or not. This is the transformed points. These are the original points. This is a linear equation I got. If I apply this, let's see if I'm getting or not. 1 into future 1 value is minus 2 plus 1 into featured value is minus 2. So minus 2 will become minus 4. Okay. 0 into 1, 0 into 1, 0. 2 into 1 plus 2 into 1 will become 4. So just look at the distance between these two. These two will be same, right? 2, 2 is 4. plus 4, that is equal to 8 root 2. Just the distance between these 2 points, all the 3 points are same, you're getting the same thing. And when you use the linear equation, you're getting the original points. So this is what actually PCA is. That's how you calculate the principal components and all those things. Now the last thing that you want to discuss is so you should be able to find out should have variance in the data, basically. Okay, should have variance in the data. If you don't have variance in the data, you cannot use principal component analysis. When to use principal component analysis, you should be able to find out the maximum direction of maximum variance. Basically, when you have the ellipsoidal data, something like this, then only you can apply the principal component analysis, because there is a variance. Okay, and that variance you are transforming that to this kind of data set. Okay, because you're trying to find out the principal component analysis. Okay, you're trying to find out the principal components, and then you're rotating the principal components. This principal component is becoming as the horizontal axis, this is becoming vertical axis. So you're transforming the points from this space to this space. That is what you're doing with principal component analysis, right? So if you don't have the variance in the data, you cannot apply principal component analysis, because you don't know whether this is principal component 1 or this is 1, this is 1. Everything has is the best representation. You don't have a single principal component or the line which actually have the most variance. When the variance is 0, and I mean when the covariance is 0 between the dimensions, you cannot apply the principal component analysis. You should have the covariance, non-zero covariance between the features, then only, or the dimensions, then only you can apply the principal component analysis. And now I also told you something about this one. I said I'll come back to this again. I mentioned that eigenvectors are corresponding to the distant eigenvectors are orthogonal to each other. Okay, I said all the principal components are orthogonal to each other is what I have told, right? So all principal components are orthogonal to each other. Why they are orthogonal to each other? Because for a symmetric matrix, all the eigenvectors corresponding to the distant eigenvalues are orthogonal to each other. For a symmetric matrix, all eigenvectors are orthogonal to each other. Okay, so from which matrix we are deriving principal components? We are deriving that from sigma, which is covariance matrix. Is covariance matrix a symmetric matrix?
Yes.
Symmetric matrix?
Yeah, because it is a positive semi-definite.
Yeah, so it is a symmetric matrix. So what is a symmetric matrix? A transpose is equal to A is called as a symmetric matrix. So if you take sigma x square, sigma xy, sigma yx, sigma xy and yx are equal. So A transpose will be equal to A. So that is a symmetric matrix. For symmetric matrix, all eigenvectors are orthogonal. That means symmetric matrix eigenvectors are principal components. So all principal components are orthogonal to each other. That's why I simply said all. I thought I asked to take that statement, saying like all principal components are orthogonal to each other. This is the reason why principal components are orthogonal to each other. Understood? Is that clear?
Yeah.
Right. So that is all about principal component analysis. So we already have understood of deriving the um, um, given a matrix, you can find out the covariance matrix. Before finding the covariance matrix, you just have to standardize the data and you have to do all that stuff. Okay. This is one thing that I would like to. We also got an example of the same thing. I don't know if you can. What is the time there? I would just want to cover one last thing, which is this one. So, this is Okay. I just want to close PCA today so that we will be left with SVD and what are the linear feature construction linear combination models, PCA, principal component analysis, singular value decomposition, and linear discriminant analysis, right? By today, we will be completed with PCA, and in the next weekend on Saturday and Sunday, we will learn SVD and LDA, linear discriminant analysis. So we are left with very simple concept with PCA, one last concept that I'll just try to explain you now. With that, we will be done. Okay, and then we can just move on to principal component analysis. There is another representation of the sigma. Okay, I hope this is recording. There is another representation of the sigma, that is, we call that as spectral decomposition of sigma. Okay. Spectral decomposition of the sigma. How can I write that is, I'm just giving this statement and then I'm going to prove it. Okay, so the sigma can be written as u okay, so sigma can be written as u delta u transpose. Okay, so this is called as spectral decomposition of sigma. So this is called as spectral decomposition of sigma. I'll talk about this in the next week as well in more detail. I'll just close this with a simple proof because we already have an example in place. So I said sigma can also be represented as, we know that 1 minus 1, we represented sigma as 1 by n minus 1 x center transpose into x, right? That is what we have seen. But it can also be represented as sigma is equal to u delta u transpose. Okay, there is a special meaning why I'm representing it this way. So, but let me explain you. U is the unit vectors of eigenvalues. Okay, U is unit eigenvectors. Okay, each eigenvector represented in this way: u1, u2, u3, and so on. So this is the eigenvector represent. Let's suppose I have three eigenvectors: 2i plus 3j, 3i plus 4j, something like this. Then that u becomes 2, 3, 3, 4. That is the eigenvector, that is u. What is delta? Delta is a diagonal matrix. You know what is a diagonal matrix, right? Diagonal matrix is nothing but all the diagonal elements will have non-zero elements. And these are the lambda 1, lambda 2, lambda 3. That means eigenvalues. Delta is a diagonal matrix where the diagonal elements are the eigenvalues. So the first eigenvector is corresponding to the first eigenvector is corresponding eigenvalue comes in the first row, or else vice versa we can say this is the first eigenvalue corresponding eigenvector will comes in the first place, and you can u transpose. Okay, so that is what basically that is actually what u delta and u transpose means. Now we have the previous example, right? So from the previous example, let's take the values and let's try to answer this. So we need these values. So what is the sigma from this? Sigma, what is a covariance matrix? 4 4 4 4 is a covariance matrix, right? So 4 4 4 4 is a covariance matrix. What is the u? U is the eigenvectors. So 1 1 minus 1 comma 1 is the eigenvector. So this becomes 1 1. What is the other one? Minus 1 and 1. So this is the u. What is the delta? Delta is a diagonal matrix with eigenvalues as the diagonal element. So this becomes 8 is the eigenvalue for the first one, right? 8 is the eigenvalue and 0 is the eigenvalue for the second eigenvector. So for the first eigenvector, corresponding eigenvector, eigenvalue corresponding eigenvector 0 minus 1 1 is the eigenvector corresponding to 0, eigenvalue 0. Now what I'll do is I'll just simply do a multiplication of all this and see what I'm getting. So u is 1 1 minus 1 1 and 8 0 0 0, and u transpose will be 1 minus 1 1 1. Okay, now let's see if I'm getting this sigma or not. So if I multiply this, 1 into 8 is 8 0. This becomes 8 minus 0, so this becomes 0, this becomes 8, this becomes 0, and this to be multiplied with 1 minus 1 1 minus 1, sorry, 1 plus 1. Is this right? Now did I do something wrong? So this becomes 8 8 8 8, right? So this is what I'm getting, right? Which is not matching to sigma. Is that right? Sigma is 4 4 4 4. I got 8 8 8 8. Where could be the wrong? I said u is the unit vector notation of the eigenvalues, right? U is unit vector notation of eigenvalues. So this becomes 1 by root 2, right? This becomes 1 by root 2 minus 1 by root 2 by root 2. So that is where the error is coming up. So everywhere root 2 will be coming up, right? So this will be root 2, this will be by root 2, this will be by root 2, this will be by root 2. And it all sums up to, this comes as 8 by root 2. This comes as 8 by root 2. So we will also have root 2 here, root 2 here, root 2 here, root 2 here. So 8 by root 2 into 8 by root 2, it all becomes by 2's. So that becomes 4 4 4 4, okay, which is matching to this. So that is the spectral decomposition of the eigen sigma, okay, u delta u transpose. As we just have the example above, we already have got I just proved that, which is spectral decomposition of the sigma. Okay, so just remember that. Now you can represent that as u1 lambda 1 u1 transpose, u2 lambda 2 u2 transpose. It is just like this one. So what can I say? uh, just go back to the previous slide. Now we know that sigma, now I know that sigma is equal to u delta u transpose, right? So now what does this become? This becomes u1, right? This is u1 vector, u11 u12 u13. This becomes u21 u22 u23, and this becomes lambda 1 lambda 1 0 0 lambda 2 2 eigenvectors. 3 into 2 is possible. No, it always be 3 into 3 only. If you have 3, you have 3. So let's take, these are all symmetric matrix actually. So sigma can be written as u delta u transpose. So I'll just take simple eigenvectors u11 u12. So this is eigenvector 1, and these are components in different dimensions, u21 u22, and then this becomes lambda 1 0 0 lambda 2, and this becomes u1 u11 u21 u12 u22. So that is this one, u11 lambda 1 u2 0. This becomes u2 dash lambda 2 u12 lambda 1 u22 lambda 2. So this is multiplied with this one, u11 u21 u12 u22. So just multiply this and summation of this. U11 lambda 1 U11 plus U21 lambda 2 U2 dash U21, right? What is this 22? This plus 22. So what does this become? U11 lambda 1 U12 plus U21 lambda 2 U22 U11 lambda 1 U12 U21 lambda 2 U22. Okay. So this is same thing. U12 lambda 1 U11 plus U22 lambda 2 U21 U12 lambda 1 U12 plus U22 lambda 2 U22. So these two are same. This is eigenvalue, right? Again, this is symmetry. This is decomposition of the covariance matrix. So these two will be the same always. That's the reason you're getting U11 lambda 1 U1 square U12. This is the one U22 lambda 2. So these two are same. So these two, this is like x component U11 lambda 1 U12 U21 lambda 1 U22. These are two second components and these are the first components of that eigenvector. Okay, in simple this can be written as each sigma will be written as sigma I is equal to 1 to dimension d lambda 1 lambda I ui into ui transpose. So 1 u1 1 transpose. Okay, I'll again talk about this in the next session. So this is just the decomposition of the sigma. If you break that to u1, u2, so you just have to understand u. What is u delta u transpose? U is the unit vector or unit vector representation of the eigenvectors. Lambda diagonal elements of lambda will be the delta eigenvalues of the covariance matrix, and u transpose is just the transpose of that. Yeah, that's all for today. Are you really